From the ground, the night sky performs a very old deception. It looks still. It looks clean. It looks so far removed from us that whatever is happening out there seems to belong to another order of reality entirely, something distant enough to admire, but not to fear, a field of light above a sleeping planet, silent, decorative, almost gentle. That feeling is wrong, because even now, with no storm overhead, no warning siren, no visible wound in the sky, Earth is being hit. Not by meteors, not by sunlight, by particles so small they disappear into abstraction the moment you try to picture them, and so energetic they can cross the galaxy, strike the upper atmosphere, and explode into a downward cascade of new particles that spread across kilometers of air before some of them reach the ground. We do not see the impact itself, we live inside the fallout. High above your head, protons and atomic nuclei moving at nearly the speed of light slam into molecules in the atmosphere and break into showers of secondary particles, muons, electrons, positrons, neutrons, gamma rays, a chain reaction of ionization raining through the sky with no sound, no color, no human-scale drama. A calm night can be full of it. Your body does not announce it. The clouds do not part for it. The stars go on looking beautiful. The night sky is not peaceful. It is merely dark. And for a long time, that darkness helped hide a much deeper fact. The universe is not only full of light, it is full of acceleration, full of places where matter is whipped to energies so extreme that the particles escaping those environments can cross interstellar space and still arrive here carrying more violence in a single atomic fragment than our most powerful machines can easily reproduce. That is what cosmic rays are. Not rays, in the usual sense, mostly charged particles. Tiny projectiles fired by processes so extreme that for more than a century, astrophysics has been forced to ask a question that sounds almost mythic and turns out to be painfully physical. What exactly is capable of doing this? Because the energy is real, the damage is real, the mystery is real. Cosmic rays can interfere with satellites, upset onboard electronics, degrade instruments, and contribute to the radiation environment that astronauts and high-altitude systems must endure. Even here on the surface, shielded by the atmosphere and Earth's magnetic field, we are still living beneath the diluted remains of an ongoing bombardment. Not an apocalypse, just something stranger than that. A permanent condition. And the unnerving part is not just that these particles exist. It is that for most of the time we have known about them. We did not know where they were coming from. The first crack in the illusion opened in 1912, when Austrian physicist Victor Hess climbed into a balloon and carried his instruments thousands of meters into the sky. At the time, the prevailing assumption was simple enough. If ionizing radiation in the atmosphere was coming from Earth, then climbing away from the ground should make it weaken. Instead, it intensified. The higher Hess went, the stronger the ionization became, not slightly, enough to break the old explanation, enough to force a reversal. The radiation was not rising from below. It was arriving from above. That moment did more than reveal a new phenomenon. It quietly destroyed a comforting boundary. It suggested that space was not a passive emptiness surrounding Earth, but an active source of intrusion. Something out there was reaching in. Something energetic enough to charge the atmosphere from the outside. Hess had discovered cosmic rays, but discovery was the easy part. Understanding them was much worse. Because cosmic rays do not arrive carrying a return address. They arrive damaged, deflected, disguised by the very journey that brings them here. They are charged particles, and charge is a problem. Between the stars, magnetic fields thread through the galaxy like an invisible maze. A particle moving through those fields does not travel in a clean straight line. Its path bends, and bends again. By the time it reaches Earth, the direction it came from may no longer point back to its source in any useful way at all. So even when the evidence is hitting your planet, the trail can already be ruined. And then the atmosphere makes it worse. The original particle usually does not survive the encounter. It strikes the upper air and breaks apart into a shower of descendants, and what detectors on the ground actually measure is not the bullet, but the debris cloud. It is like trying to identify a weapon after it has already hit a wall, vaporized, and filled the room with fragments. For more than a century, Scientists have been looking at those fragments and trying to reconstruct the hidden engine that launched them. That is the real beginning of this story. Not a hunt for an impressive object, not a ranking of cosmic monsters, a forensic problem, a trail of violence arriving broken, evidence without a clean line back to the scene of the crime. And yet even broken evidence can tell you things, if you collect enough of it. One of the first things scientists learned was that cosmic rays come in a staggering range of energies. Some are energetic by human standards. Others are so extreme that even the numbers begin to lose emotional meaning. Millions of electron volts. Billions. Trillions. Quadrillions. At those scales, the ordinary language of power starts to fail. Because nothing in daily life prepares you for the idea that a single, subatomic particle can carry energy levels that put nature's own accelerators in a category our machines only gesture toward. This is where the story stops being merely technical and starts becoming unnerving. Because if a particle reaches Earth carrying that much energy, then somewhere in the universe, something had to give it that energy. Energy does not appear by permission of our curiosity. It has to be transferred, built up, forced into matter by real conditions, real fields, real shocks, real gravity, real magnetic violence. Somewhere, there must be an astrophysical environment capable of taking an ordinary particle and driving it to near unthinkable speeds without tearing the process apart first. That means cosmic rays are not just stray visitors from space. They are proof that the universe contains engines more severe than the sky suggests. And the contradiction is easy to miss because our senses are so badly adapted to the actual terms of the cosmos. Human perception is built for surfaces, temperatures, moving bodies, visible danger. It reads the stars as points of light suspended in stillness. It does not read magnetic fields. It does not read ionization. It does not read relativistic particles crossing interstellar distances. It does not read the sky as a battleground of invisible trajectories. It reads quiet, where physics is busy. That is why cosmic rays matter so much. They are one of the clearest reminders that reality is not arranged around what feels intuitive from the ground. The visible universe is only the skin of the thing. Behind that skin is a harsher architecture, pressure, turbulence, shock fronts, collapsing stars, trapped plasma, magnetic reconnection, jets, winds, an environment so extreme that matter can be hurled outward, carrying energies our species still treats with a kind of procedural awe. And somehow, some fraction of that violence reaches us. Not as spectacle, as residue. That word matters. Residue. Because what reaches Earth is almost certainly not the full event. It is the leak, the overspill, the surviving trace of processes unfolding elsewhere at scales of density, velocity, and magnetic intensity that do not announce themselves to the naked eye. By the time the signal touches our atmosphere, most of the story is already missing. Which means the real mystery was never just that we were being hit. It was that we were being hit by evidence from places we could not yet see clearly, produced by mechanisms we did not yet understand, arriving in forms that actively concealed their own origin. For 100 years, the galaxy has been firing clues at Earth, and for most of that time, we were reading the damage without knowing the weapon. That is what makes this search so gripping. Not the romance of distant objects, the humiliation of human intuition, the realization that a sky that looks serene can be saturated with incoming evidence of extreme physics, and that one of the great scientific tasks of the last century has been learning how to extract a hidden map of the universe from particles that arrive broken. Because once you accept that, the old image of the Milky Way begins to fail. It is no longer enough to think of our galaxy as a scattering of stars drifting in darkness. That picture is visually true and physically incomplete. Beneath it is another Milky Way, one made not of what shines, but of what accelerates. A galaxy threaded with invisible fields, sudden shocks, compact remnants, violent outflows, and natural machines capable of pushing matter to the threshold where explanation starts to feel less like description and more like exposure. But before any of those machines could be found, scientists had to confront a more basic problem. The particles reaching Earth were real. Their energy was undeniable. And yet the trail back to their source kept vanishing. Because the trail did not just vanish once. It vanished at every stage. A cosmic ray seems At first glance, like the simplest kind of clue, something arrives, so something sent it. But almost everything about these particles conspires against that logic. They are evidence that has been scrambled by distance, by magnetism, by collision, and finally by our own location inside an atmosphere thick enough to protect us from the original blow, while also destroying much of the information we would need to solve it. By the time a cosmic ray becomes measurable, the universe has already tampered with the scene. The first distortion happens long before Earth enters the story. Space is not empty in any meaningful physical sense. It is structured, threaded with magnetic fields stretched across interstellar gas, around stellar remnants, through spiral arms, across the wider architecture of the galaxy. A charged particle moving through that environment does not travel like light. It does not cut a clean line from source to observer. It swerves, it spirals, it scatters through a vast invisible geometry that can turn a direct path into something more like drift through a maze. So the most obvious question, where did it come from, is also the first one the particle refuses to answer. If you could see the true route of a high-energy proton crossing the galaxy, it would not look like an arrow. It would look like memory being corrupted. That alone would have been enough to make cosmic rays frustrating. But then they hit the atmosphere. And the atmosphere, which protects almost everything alive on Earth from direct exposure to the worst of this bombardment, is also a spectacular destroyer of clean evidence. The incoming particle collides with a nucleus high in the air. The collision produces new particles. Those particles decay or collide again. The cascade multiplies. A single visitor from deep space becomes an expanding shower. A spreading cone of secondaries rushing downward, each one carrying only part of the original event, each one telling a slightly different fragment of the story. What reaches the ground is not the particle that crossed the galaxy. It is what the atmosphere made of it. That difference is the entire problem. Because once the original particle is gone, everything becomes reconstruction. Scientists measure the shower front, the timing, the direction, the density of particles on the ground, the amount of light produced, the muons buried deeper in the cascade, the lateral spread across detectors. From those traces, they try to work backward, not only to estimate the energy of the original cosmic ray, but even to infer what kind of particle it was in the first place. A proton leaves one statistical signature, a heavier nucleus leaves another. Gamma rays create a different sort of shower again. But these are not neat labels attached to individual arrivals. They are patterns extracted from chaos, from distributions, from the shape of an event that has already broken apart overhead. It is less like catching a bullet than like reconstructing a glass sculpture from the sound it made when it shattered. And this is why the mystery endured. Not because the universe was stingy with evidence. The evidence was everywhere. It was raining through the atmosphere every second. But most of it arrived as aftermath. A century of measurements did not produce a map of clean origins. It produced a strange, accumulating pressure, a sense that the sky was full of extreme energy. Yet the identities of the engines behind it remained partially obscured by the very laws that governed their motion. That pressure grew sharper once scientists began to realize that cosmic rays were not all variations on one theme. Their energies span an enormous range. At lower energies, the flux is high enough that detectors can see them constantly. Raise the threshold, and the numbers begin to thin. Raise it further, and they become rare enough to feel almost fictional. By the time you're dealing with the most extreme events, you're no longer talking about a steady stream. You're talking about particles so uncommon that, over a given patch of ground, one might arrive only after years, decades, even longer depending on the energy scale. The universe does not hand over its most violent evidence generously. It makes you wait. That waiting shaped the entire field. You could not solve this problem with one elegant instrument on a lab bench. You had to think geographically. You had to spread detectors over huge areas. You had to measure the atmosphere itself as part of the experiment. You had to accept that, in high-energy astrophysics, rarity is not an inconvenience. It is part of the phenomenon. And beneath all of that sat an uglier realization. Even if you built a detector large enough and patient enough and clever enough to collect the debris, there was still no guarantee the debris would point home. This is where the emotional texture of the problem changes. At first, cosmic rays sound dramatic in the obvious way. Particles from space hitting Earth at extreme energies. But the deeper drama is colder than that. It is the feeling of confronting a real, measurable effect whose cause is hidden not by ignorance alone, but by physics. The particles have been bent by magnetic fields because they are charged. They have been transformed by the atmosphere because collisions are inevitable. The source is not simply far away. The source is veiled by the lawful behavior of the evidence itself. Reality is not keeping a secret. Reality is behaving normally, and normal behavior is what makes the secret hard. For decades, that lawful obscurity left astrophysicists in an uncomfortable position. They knew the galaxy was producing extraordinary particles. They knew some of those particles reached energies far beyond anything ordinary stellar processes would casually explain. They knew the origin could not be random, and yet every attempt to point directly at the source ran into the same problem. By the time the signal arrived, too much of the geometric truth had been lost. So the field learned to stop asking for a clean route and start asking different questions. Not, where is the exact source of this individual particle? But, what does the overall population look like? How many particles arrive at each energy? How quickly does that number fall off? Does the slope change? Do different energies imply different astrophysical populations? When direct tracing fails, structure has to be extracted statistically. The mystery shifts from a chase scene to a pattern problem. And that is where one of the strangest features in all of high-energy astrophysics begins to matter. If you plot the number of cosmic rays against their energy, the distribution is not smooth forever. There is a bend in it, a steepening, a break, a place where the flux drops more sharply than the lower energy trend would predict. It is known as the knee, and it sits like a pressure point in the spectrum, a shape hinting that something changes there. Maybe acceleration is becoming harder. Maybe a dominant source class is reaching its limit. Maybe confinement inside the galaxy begins to fail differently. Maybe several mechanisms overlap and part ways. The curve does not explain itself. But it does tell you this much. The universe is not accelerating particles with one simple, uninterrupted logic all the way up. Somewhere near that bend, something gives. That mattered because it offered something the individual particles could not a direction, but a clue about structure, a clue that the mystery might not be solved by catching one perfect event, but by understanding where the population thins, where the spectrum hardens or softens, where the hidden machinery of the galaxy leaves an imprint on a graph instead of a sky map. It was a subtler kind of evidence, less cinematic, more dangerous, because once the answer moved into the spectrum, the problem stopped being just observational and became interpretive. The curve was no longer a measurement alone. It was a boundary marker, a statement that at certain energies the galaxy might be revealing the limits of its own accelerators, or at least the limits of the ones we had imagined so far. And that carried an implication no one could ignore. If the spectrum bends, then the engines behind it are not all equal. Somewhere above the ordinary storm of incoming particles, there had to be sources capable of pushing matter higher than most, higher than expected, higher, perhaps, than the standard suspects could comfortably explain. The evidence still arrived broken, but now the fracture itself had a shape. And once the fracture had a shape, the mystery became harder to dismiss as mere observational inconvenience. A century of failed tracing can still be explained away as insufficient technology. A distorted signal can still be blamed on distance, bad luck, incomplete data. But a feature in the spectrum is different. A feature means structure. It means the confusion is not random. Somewhere inside the apparent disorder, the galaxy is leaving behind a controlled pattern. That changed the emotional weight of the problem. Because the knee in the cosmic ray spectrum is not just a bend in a graph. It is a place where an old picture of the universe starts to strain under its own assumptions. As the energy rises, the number of incoming particles falls. That much is expected. Extreme events should be rarer than ordinary ones. But near a few peta-electron volts, around 1,000,000 billion electron volts, the decline steepens more sharply. The population thins faster than the lower energy trend says it should. Something is happening there. Maybe certain galactic accelerators are hitting their ceiling. Maybe lighter particles drop away first while heavier nuclei continue higher. Maybe the magnetic architecture of the Milky Way becomes less able to confine the most energetic particles. Maybe what we are seeing is not one process ending, but several processes handing the problem off between them like runners disappearing into fog. Whatever the detailed explanation turned out to be, the NIE said one thing with unusual confidence. The galaxy is not accelerating particles indefinitely under one simple rule. There is a threshold, a change of regime, a hidden transition written not in words but in scarcity. And scarcity is where the search became brutal. At lower energies, cosmic rays are plentiful enough that the atmosphere is practically full of their secondary debris. By the time you reach the energies near the NIE and above it, everything changes. The particles are no longer a constant background. They become events, singular, infrequent, statistically expensive arrivals. Each one matters. Each one is too rare to waste. Each one carries information from a regime of astrophysics, where ordinary observation starts to fail and patience becomes part of the instrument. This is one of the strangest pressures in high-energy astronomy. The more important the particle, the less often nature lets you see it. For the most extreme cosmic rays, the waiting becomes almost insulting. Over 1 square kilometre of Earth, at the very highest energies, you might expect fewer than one arrival in a century. Not because the universe lacks power, because these energies belong to a population so sparse that detecting them means building observatories that think in landscapes instead of laboratory rooms. This is where the scientific problem begins to acquire physical scale. You cannot solve a century-long mystery about rare particles with a delicate apparatus hidden inside a building. You need exposure, altitude, area. You need to sit under the sky with something vast enough to intercept a fleeting shower when it finally breaks overhead. And even then, size alone is not enough, because the real challenge is not just detection, it is diagnosis. You have to catch enough of the shower to reconstruct the parent particle, and you have to do it from evidence that is already diluted across time, angle, and debris. The detector has to be large because the universe is stingy. It has to be intelligent because the atmosphere is destructive. That combination, rarity above, wreckage below, shaped the modern search for the sources of cosmic rays more than any one theory ever did. It forced astrophysics into a kind of forensic humility. Before you could decide what object was responsible, you first had to accept what kind of evidence nature was willing to give you. And for a long time, the answer felt inadequate. Scientists could study extensive air showers. They could measure how many secondaries reach the ground. They could compare models, estimate energies, infer compositions, refine the spectrum. They could see the NIE. They could argue over whether it marked the limit of galactic accelerators or the beginning of something extragalactic. They could build increasingly sophisticated pictures of how the population behaved, but the sources themselves still remained strangely out of focus. It was like hearing distant artillery for decades and knowing from the force of the impact that the guns must exist, while still being unable to point to the ridge they were firing from. That uncertainty produced one of the field's most persistent temptations, to interpret the NIE too quickly. Some took it as a border, the place where cosmic rays from within the Milky Way give way to particles coming from beyond it. That was a clean story, elegant, intuitively satisfying, a local contribution fading out, an extragalactic population taking over. It gave the bend a grand narrative arc. But clean stories have always had a bad track record in high-energy astrophysics. The problem was that the data did not force that interpretation cleanly enough. The NIE could mean many things, and the more closely scientists studied the underlying composition and the energy dependence of different particle groups, the more complicated the picture became. What looked like a single frontier might instead be a layered handoff, different nuclei, different source limits, different transport effects through the galaxy. Not one clean wall, but a changing mixture of ceilings. That was the deeper frustration. The spectrum was clearly saying something profound, but it was not saying it in plain language. It was telling us that our model was incomplete without telling us which part was wrong. And that is often where science becomes psychologically difficult, not when nothing is known, but when the evidence is real enough to destabilize confidence and still too incomplete to restore it. The NIE was not an answer. It was a wound in the old picture, a compression point where several possibilities crowded together and refused to separate. So the field kept widening its reach. Larger detector arrays, higher altitude observatories, better discrimination between different shower components, better statistical reconstruction of primaries, more careful attempts to distinguish hadronic cosmic rays from gamma-ray events. Because if the charged particles themselves would not preserve a clean line back to the source, maybe some associated signal would, maybe some other messenger could survive the journey without being bent into nonsense. That hope mattered because the charged particles were trapped in a basic contradiction. They were the phenomenon of interest, but also the least cooperative guide to their own origin. To follow them directly was to chase something that had spent thousands or millions of years being deflected by magnetic fields, and then annihilated into a shower over your head. Every individual detection was therefore both precious and compromised. You could measure the consequence, but not the root. You could count the impact, but not yet draw the map. And in that gap between consequence and map, the century stretched on. The sky kept sending particles. The atmosphere kept breaking them apart. The spectrum kept hinting at limits. And the Milky Way kept withholding a clean picture of what kind of engines could actually be responsible. That is the point where the search stopped being just a mystery about origin and became a test of method. It asked whether astrophysics could do something far more difficult than spotting a bright object in the sky. It asked whether we could infer an entire hidden layer of galactic reality from damaged arrivals, rare statistics, and one stubborn bend in a curve. Because if the knee was real, and it was, then somewhere above that threshold lived a regime of acceleration more extreme than ordinary intuition was prepared for. A regime in which the standard suspects might fail, or fail partially, or need to be understood with much more precision than before. And to reach that regime, scientists needed a detector built not for beauty, but for attrition. Not something elegant in the human sense. Something patient enough to wait for particles the universe releases only reluctantly, and large enough to catch the wreckage when they finally arrive. That is why the next leap in this story did not begin with a new theory. It began with a mountain. A mountain, because at some point the problem became too large for ordinary scale. If the rarest particles only reveal themselves through the wreckage they create in the atmosphere, then every meter of altitude matters. The higher your observatory sits, the closer it is to the first stages of the shower, before the evidence has spread too thin, before too many of the secondary particles have decayed away, before the geometry of the event has become harder to reconstruct. And if the most important particles arrive so infrequently that a square kilometre might wait years for a meaningful handful, then every metre of area matters too. The search for the highest energy cosmic rays was always going to become architectural. You do not solve this kind of mystery with a better lens. You solve it by occupying more of the sky's fallout zone. That was the logic behind a new generation of observatories, and one of the most decisive among them rose high in the mountains of Sichuan, in China, nearly 4,500 meters above sea level. The Large High-Altitude Air Shower Observatory, LHAASO, was built for a very specific kind of difficulty. Particles so energetic and so rare that they force science to become patient at continental scale. Everything about it reflects that pressure. The altitude is not cosmetic. At that height, the atmosphere above the detector is thinner, which means the particle showers can be sampled closer to their development, before too much of the original structure is lost. The size is not extravagance. It is an admission that the most extreme events do not arrive often enough for small instruments to catch them reliably. And the design is not just about counting impacts. It is about separating kinds of evidence from one another. The electromagnetic components of a shower, the muons, the timing, the footprint, so that the parent particle can be inferred with something better than guesswork. LHAASO is not watching the sky in the ordinary sense. It is reading the ground for consequences. That distinction matters, because by the time a cosmic ray event becomes measurable, what exists above the detector is no longer a single incoming particle, but a spreading catastrophe of secondaries racing through the air. A useful observatory has to catch enough of that catastrophe to work backward. How energetic was the original particle? What direction did the shower come from? Was the parent likely a proton, a heavier nucleus, or something else entirely? Did the event begin with a hadronic cosmic ray, or was it triggered by a gamma ray? Those are not decorative questions. They decide whether you're merely recording that the universe is violent, or actually learning what kind of engine is producing the violence. And this is where the modern search began to sharpen. For years, the cosmic ray problem had suffered from a cruel asymmetry. The particles were real, their effects were measurable, the spectrum contained structure, but the field still lacked a clean enough way to isolate the most important arrivals from the overwhelming confusion of everything else. High-energy gamma rays, in particular, were tangled up in the larger storm of ordinary hadronic showers. To see the rare signal you cared about, you first had to reject an immense background of signals that looked similar from a distance, and only began to separate when your detector became sensitive enough to read their internal anatomy. That is one of the reasons LHAASO mattered so much. It was not just big, it was selective. Its interconnected detector systems were designed to distinguish one kind of event from another, to turn air showers into something like identifiable signatures. The shower particles hitting the surface array could reveal the spread and direction. Underground or shielded detectors could help pick out muons, which are abundant in hadronic showers and comparatively scarce in gamma-ray-induced ones. Water Cherenkov measurements could capture the light produced when fast particles moved through water, adding another layer of timing and energy information. The result was not perfect certainty. Nothing in this field gets that luxury, but a dramatic increase in discrimination. For the first time, the search was not only broad enough to catch the rarest fallout, it was sharp enough to ask what that fallout actually was. And then, before the instrument was even fully complete, the sky gave back something astonishing. It did not arrive as a neatly labelled revolution. It arrived in the language high-energy astrophysics trusts most: an event, then another, then a pattern too extreme to shrug away. LHAASO detected gamma rays with energies exceeding 1 peta-electron volt, a quadrillion electron volts. The number is easy to recite and almost impossible to feel. At human scale, it sounds like arithmetic pushed past relevance. But in physical terms, it is a declaration. A gamma-ray photon at that energy is not a curiosity. It is evidence that somewhere, some astrophysical environment has accelerated particles to a level that decades of theory had treated as a threshold of almost mythic importance. This was not just very energetic. It was regime-changing. To understand why, you have to be careful about what a gamma-ray is actually telling you. The gamma-ray itself is not necessarily the original accelerated particle. More often, it is a consequence, a product of other particles being accelerated and then interacting with fields, photons, or matter. But energy conservation does not negotiate. If you detect a photon carrying around a peta-electron volt of energy, the process that produced it had to draw on a source of at least that scale, usually more. A photon like that is downstream evidence of an accelerator operating in a domain far beyond what most known galactic objects had ever been confidently shown to achieve. For decades, astrophysicists had used a name for hypothetical sources capable of accelerating particles to peta-electron volt energies: Pevatrons. It was a useful word because it marked a boundary, not just any energetic object. A source strong enough to push particles into the Pev range, the region around the knee, the region where the cosmic ray mystery hardened into a real structural problem, the region where ordinary explanations began to strain. Pevatrons had been discussed, modelled, guessed at, and indirectly invoked. But indirect belief is not the same thing as observational consequence. Once LHAASO started seeing photons at those energies, the category changed. Pevatrons were no longer theoretical placeholders. They were part of the observed universe. One detected photon in particular pushed the point almost brutally, around 1.4 peta-electron volts, the highest energy photon ever observed at the time. Put beside the particles accelerated in human-built colliders, the comparison became almost embarrassing. The Large Hadron Collider is one of the most sophisticated machines our species has ever constructed, a triumph of engineering, precision, and collective organization. And yet nature had produced, somewhere in our own galactic environment, a process capable of handing a single photon vastly more energy than the fastest protons accelerated in that machine. The lesson was not that human engineering is small. The lesson was that astrophysical violence has scales our technology has only begun to approach in fragments. And that changed the search in a second, more subtle way. Cosmic rays themselves had always been difficult witnesses. Charged particles bend. They lie about their route without meaning to. But gamma rays are neutral. They do not respond to magnetic fields the same way. They travel, in the simplest approximation, in straight lines. That means a sufficiently energetic gamma ray does something the charged cosmic rays generally cannot. It points. Not perfectly, not with infinite precision, but enough to turn the mystery from pure fallout analysis into directional astronomy. Enough to say that somewhere along this line of sight, there is an engine severe enough to produce the observed event, enough to transform the problem from the galaxy contains hidden accelerators into some of those accelerators may now be locatable. This was the first real tightening of the net, and it came with a strange emotional inversion. For years, the highest energy cosmic ray problem had seemed vast because the possible origins felt unconstrained. A particle might have crossed enormous distances, bent through magnetic fields, wandered through the galaxy, then died in the atmosphere over your detector. But a gamma ray at these energies could preserve direction. Suddenly the sky stopped feeling like a generalized source of violence and started acquiring specific lines of accusation. LHAASO began to identify distinct regions associated with ultra-high energy gamma ray emission. Not one vague glow, not a formless background, actual candidate sources, places in the sky where nature appeared to be accelerating particles into the Pev regime or beyond. But even that triumph contained a limit, because a direction is not yet a distance, a line of sight is not yet an object. A bright signal can still conceal multiple possibilities layered along the same patch of sky. The search had become narrower, but not narrow enough. The evidence now refused to bend, but it still had not fully confessed where it came from. Then physics intervened again, and this time it made the universe smaller, because a straight line through the sky still leaves one intolerable ambiguity. It tells you where to look. It does not tell you how far away the culprit is. And in astronomy, that difference is everything. A line of sight can pass through nearby gas, distant remnants, pulsars, binary systems, star-forming regions, and background structures all stacked along the same apparent patch of sky. Direction narrows the mystery. It does not solve it. If you're trying to identify the engine behind an ultra-high energy gamma ray, somewhere along this line is progress, but it is still a very large amount of ignorance. So for a brief moment, the search occupied an awkward in-between state. LHAASO had done something remarkable. It had found evidence that Pevatrons were real and had begun to map candidate directions across the sky. But the deeper question remained suspended. Were these sources inside our own galaxy, on its far side, beyond it? Were we looking at local accelerators or at much more distant engines whose photons had somehow reached us intact? Then another law of physics tightened the hunt. Because gamma rays, powerful as they are, do not move through the universe unchallenged. Space is not a clear vacuum through which any photon can travel forever if it is energetic enough. It is filled with background light, a vast bath of lower energy photons left over from the history of the universe itself and from the accumulated glow of stars and dust. Most of those photons are cold, weak, innocuous by human standards. But to an ultra-high energy gamma ray, they are enough. At sufficiently high energies, a gamma ray can collide with one of these background photons and vanish. Not dim, not scatter slightly. Vanish into a new pair of particles, typically an electron and a positron, converting the original gamma ray's energy into matter. The process is one of the strangest forms of censorship in astrophysics. A photon can leave an extreme accelerator carrying absurd energy and still fail to cross the full depth of space, not because it runs out of momentum, but because the universe is crowded enough with low-energy light to kill it. That means an ultra-high energy gamma ray comes with a built-in distance limit. The more energetic it is, the less far it can travel before the probability of destruction becomes overwhelming. So when LHAASO began detecting gamma rays in the peta-electron-volt range, those photons did not merely indicate powerful sources, they also imposed a geographic restriction. Such photons could not have wandered across cosmological distances from some remote galaxy on the far edge of the visible universe. They were too fragile for that, despite their violence. The same energy that made them extraordinary also made them vulnerable to annihilation in transit. And suddenly the search volume collapsed. Those candidate sources were not just somewhere in space. They were almost certainly here, inside the Milky Way. This was one of the quietest and most important reversals in the whole story. For years, one tempting interpretation of the cosmic ray spectrum had been that the knee might mark a transition between galactic and extragalactic origins, that above a certain energy, perhaps the Milky Way was no longer the main actor. It was a clean idea, reasonable, elegant in the way many partial truths are elegant before better evidence arrives. But PEV gamma rays forced a more intimate conclusion. If the photons were reaching Earth at those energies, then the accelerators producing them had to be nearby in cosmic terms. Nearby enough to survive the trip. Nearby enough to exist within our own galactic structure. The mystery did not open outward into the wider universe. It folded inward. The line pointed away from Earth. Physics drove it back home. And that changed the emotional scale of the problem more than any raw energy number could. Because it is one thing to imagine that the most severe particle accelerators in nature belong to some distant class of exotic galaxies, safely abstract, beyond any felt connection to the familiar night sky. It is another thing entirely to realize that the engines behind these particles may be embedded in the same galaxy that forms the pale river overhead on dark nights. The same Milky Way that human beings have spent millennia turning into mythology, navigation, ornament, and atmosphere. The same visible band that looks serene precisely because our senses are blind to the processes that matter most here. The question was no longer what distant monstrosity might produce such energies. It became, what, in our own galaxy, is capable of this? That narrowed the field, but it also made the stakes sharper. Once the search became galactic, the candidate classes of source had to be evaluated more seriously, more physically. Not every bright object could qualify. Not every violent environment could accelerate particles to the required energies, and not every source that could, in theory, reach the PV scale would necessarily leave the right observational signature. The problem had moved from speculative grandeur into mechanism. That is where astrophysics becomes less romantic and more dangerous to intuition. Because what the search needed now was not just a list of energetic objects. It needed actual acceleration channels, ways for matter to gain energy in stages, to remain confined long enough to keep gaining it, to escape at the right time, to interact with surrounding material or radiation fields in ways that would produce the gamma rays we observed. A source does not become a Pevatron by being dramatic. It becomes one by solving a precise physical problem. How do you take a charged particle and drive it to a quadrillion electron volts before losses, escape, or instability cut the process short? That question begins to sort the galaxy into a harsher taxonomy. Supernova remnants rose immediately to the front because they had been the leading suspects for decades. A star explodes. The ejected material plows into surrounding space, and a shock front forms, a collisionless boundary where density, pressure, and magnetic structure change abruptly. Under the right conditions, charged particles can cross that shock front again and again, scattering off magnetic irregularities, gaining a little energy each time. It is a brutal, elegant process, not one giant kick but repeated theft from a moving front, diffusive shock acceleration, first-order Fermi acceleration, one of the central ideas in high-energy astrophysics. It sounds almost modest when described in words. In reality, it is one of the ways the universe turns violence into spectrum. A particle trapped near such a shock does not simply pass through and leave. If the magnetic conditions are favourable, it can bounce back and forth across the boundary many times. Every crossing offers another chance to gain energy. Stay trapped long enough, and the particle climbs, not infinitely, not effortlessly, but enough to explain a great deal of what we see in galactic cosmic rays. That is why supernova remnants were so attractive as candidates. The raw energy budget was there. If even a fraction of the kinetic energy of an exploding star could be transferred into accelerated particles, the galaxy's cosmic ray population might be largely accounted for. It was a powerful idea because it connected something already known to be common and violent with something already known to be arriving at Earth. But the closer the field pushed toward the PEV frontier, the more the question sharpened. Could supernova remnants really do it all the way? Could they reach the energies needed near the knee, especially for protons and nuclei, not just in broad principle but in actual observed systems? This is where the search stopped being satisfied with plausible energy and began demanding timing, confinement, and evidence. Some models suggested that supernova remnants might only reach their most extreme acceleration potential very early in life, when the shock is strongest and the magnetic environment most favourable. A brief window, perhaps the first 100 years or so. After that, the remnant expands, the shock weakens, conditions change, and the ceiling drops. If that is true, then the best Pevatron phase of a supernova remnant is also the easiest phase to miss. By the time we notice the remnant clearly, its most violent acceleration era may already be over. That possibility did not eliminate supernova remnants, it made them more subtle. Some could still be illuminating nearby molecular clouds with particles accelerated earlier. Some could still be contributing heavily to the galactic cosmic ray population. Some of LHAASO's candidates could plausibly be associated with them. But the closer the field moved toward the strictest interpretation of a Pevatron, a source actively driving particles into the Pev regime now, the less comfortable it became to let one familiar source class carry the entire burden of explanation. And once that doubt appeared, another class of object moved into clearer focus. Not exploded stars. What they leave behind. What a supernova leaves behind is not a corpse in the ordinary sense. It is a compression of physics. A neutron star is what remains when a massive star dies, and gravity wins almost all the arguments. The core collapses so violently that protons and electrons are crushed together into neutrons. A stellar mass is forced into a sphere barely the size of a city. The density becomes so obscene that matter stops feeling like matter in any human sense. And if that remnant is rotating rapidly and carrying an immense magnetic field, it enters the story under a more specific name. A pulsar? Few objects in astrophysics make the universe's priorities clearer. A pulsar does not glow because it is picturesque. It glows because enormous rotational energy is being bled away through electromagnetic violence. It spins. It magnetizes the surrounding space so intensely that charged particles cannot treat the region around it as empty. The star becomes a machine for generating electric fields, launching winds, and reorganizing matter in its vicinity into something far more extreme than a quiet remnant cooling in darkness. If supernova remnants taught astrophysics to think in shock fronts, pulsars forced it to think in winds. And winds, under the right conditions, can accelerate particles ferociously. The logic begins close to the star, where rotation and magnetism combine into a brutal electromagnetic engine. The magnetic field co-rotates with the neutron star, dragging the surrounding plasma into a highly energized environment. Electric fields can rip charged particles from the stellar surface or from pair cascades in the magnetosphere, feeding an outflow of electrons and positrons that streams away at relativistic speed. This is the pulsar wind, not a breeze, but a torrent of high-energy particles launched into surrounding space. For a while, that wind expands outward almost freely. Then it hits resistance. The surrounding nebula, ejector, or ambient medium pushes back. The flow decelerates abruptly. A termination shock forms, a boundary where an ultra-relativistic outflow is forced to slow, compress, and reorganize. And once again, astrophysics finds one of its favorite structures, not a static object, but a place where kinetic energy, magnetic structure, and confinement combine into an accelerator. The shock is where the wind begins to surrender energy. The particles are where that energy goes. This is one of the most important conceptual turns in the story, because it reveals that the highest energy environments in the galaxy are not always obvious in visible light. A pulsar may look like a point source, a nebula may look like a diffuse glow, but the true drama lies in the invisible architecture between rotation, magnetism, and plasma flow. Power in the universe is often not a matter of brightness. It is a matter of transfer. How efficiently can an environment take ordered energy, rotational, magnetic, gravitational, and force it into particles before the system leaks, cools, or collapses into a less useful state? Pulsars are good at this question. Very good. Long before the term Pevatron became observationally urgent, pulsars had already established themselves as plausible accelerators of electrons and positrons to extreme energies. We know their winds are real. We know their nebulae shine across the electromagnetic spectrum. We know the environments around them are loaded with magnetic pressure, shocks, turbulence, and relativistic particles. The theoretical appeal was obvious. If any compact galactic object could continue to energize matter long after the original supernova blast had expanded and softened, it would be something like this. A rotating neutron star is a long afterlife for violence. And compared to a supernova remnant, a pulsar offers a different kind of continuity. The remnant's shock can weaken as the system ages, but a pulsar can keep injecting energy into its surroundings over much longer timescales, though not forever and not without losses. That made pulsar wind nebulae increasingly attractive in the search for the sources behind ultra-high energy gamma rays. Several of LHAASO's candidate regions appeared consistent with such systems. The implication was hard to ignore. Maybe the galaxy's most powerful particle engines were not just the shells of exploded stars, but the compact electrodynamic remnants still spinning inside or near them. But the closer you look, the harder the question becomes. Because once again, energetic is not enough. A pulsar can accelerate electrons, that part is well supported. Yet the deepest cosmic ray problem is not merely about electrons. The majority of cosmic rays reaching Earth are hadrons, mostly protons and nuclei. That distinction matters because the physics of radiative loss changes everything. Electrons are light. They radiate efficiently. They lose energy fast through synchrotron emission in magnetic fields and through inverse Compton scattering off background photons. In practical terms, electrons are brilliant but fragile. They can be driven to immense energies, but keeping them there is difficult because they bleed energy away almost as soon as they gain it. So when a pulsar wind nebula is seen producing very high-energy gamma rays, one major interpretive challenge immediately appears. What is being accelerated, and how do we know? If the gamma rays come from electrons upscattering lower-energy photons, that proves an extraordinary electron accelerator, but it does not automatically solve the hadronic cosmic ray mystery. To explain the protons and nuclei bombarding Earth, the galaxy needs sources that can accelerate hadrons as well. The observational signatures can overlap. The consequence is subtle but fundamental. Not every object capable of generating PeV gamma rays is necessarily the kind of source that explains the bulk of cosmic rays we care most about tracing. This is where the story grows teeth. Because the search for the most powerful object begins to split into stricter categories. One source may be a phenomenal electron accelerator, another may be a hadronic powerhouse, another may mimic one while hiding the other. The word Pevatron remains useful, but the closer science gets to actual sources, the less that single label feels like a final answer. It marks a threshold, not a complete identity. Still, some objects force themselves forward by sheer extremity. The most famous of them was already hiding in plain sight. The Crab Nebula has been studied so intensely that it can feel almost overfamiliar. A staple of astrophotography, a relic of a supernova recorded by human observers nearly 1,000 years ago, a luminous tangle in the constellation Taurus. But familiarity is one of astronomy's most dangerous filters. It can make something seem understood simply because it is famous. In reality, the Crab is one of the most severe particle environments we have ever examined in detail. At its center sits the Crab Pulsar, driving an energetic nebula that shines across the spectrum. The system has long served as a natural laboratory for high-energy astrophysics because it is close enough, bright enough, and structured enough to let us test ideas about shock acceleration, magnetic reconnection, and radiative processes under extreme conditions. Then came the gamma-ray flares. They were the kind of observation that resets your sense of proportion. Sudden episodes of intense gamma-ray emission lasting hours to days, implying that electrons in the nebula were being pushed to energies so high and so quickly that the usual severe language of astrophysics began to feel too soft. To produce gamma rays reaching toward the PeV regime, the electrons themselves had to be accelerated to even higher energies still. And electrons are the most difficult particles to push this far precisely because they are constantly losing energy as they move through strong magnetic fields and radiation backgrounds. So if the Crab could do it, then the acceleration mechanism had to be ferocious, not merely persistent, not merely energetic, ferocious enough to outrun loss. That is an extraordinary standard. It means the Crab Nebula is not just an interesting remnant. It is a proven natural accelerator operating in a regime no human machine can reproduce as a full environment. The precise mechanism behind its most violent flares remains debated: shock acceleration, magnetic reconnection, perhaps more intricate dynamics inside the wind itself. But the broader conclusion is unavoidable. The Crab is capable of driving electrons into the PeV domain. It is beyond serious doubt a Pevatron in the electronic sense. And yet even here, at one of the field's great triumphs, the deeper cosmic ray problem remained only partially solved. Because the Crab demonstrates that nature can accelerate electrons to absurdity, the harder question is whether it is doing the same for protons. This is not a technical footnote, it is a threshold of meaning, If you're trying to explain the invisible bombardment that first fractured the peaceful sky, an electron accelerator is not automatically enough. What reaches Earth as cosmic rays is overwhelmingly hadronic. The universe may be full of environments that can make electrons blaze, but the sources we truly need are the ones that can hurl protons and nuclei to comparable scales. That is why the search did not end with the Crab. In a way, the Crab made the standard harsher. It proved that PEV-scale acceleration was real inside the Milky Way. But by proving the easier version so dramatically, it sharpened the absence of the harder one. The galaxy could no longer plead incapacity, it could only plead complexity. And complexity was starting to pile up in one part of the sky more than others. A region where multiple violent systems overlapped. A region so rich in high-energy activity that even after the search gained direction, the source still had to be teased out from competing possibilities. A region where, for the first time, the signal itself began to keep time. A direction tells you where to look. A clock tells you what to believe. That was the difference. Up to this point, the search had been narrowing through inference. Gamma rays had restored something like direction to a problem cosmic rays had spent a century ruining. Their limited travel range had forced the search inward, trapping the likely sources inside the Milky Way. Candidate classes had begun to harden. Supernova remnants, pulsar wind nebulae, perhaps more exotic environments under the right conditions. But one deep frustration remained. A line across the sky is still only a line. In a galaxy crowded with overlapping structures, the same direction can hide multiple engines stacked at different distances, embedded in different environments, all capable of producing some high-energy signal. The search had become sharper. It had not yet become decisive. And nowhere did that ambiguity feel more severe than in Cygnus. Even to the naked eye, Cygnus is one of the sky's great recognizable forms. The Northern Cross stretched over the summer sky, a familiar pattern laid across the dark, but familiarity, again, is a trap. Because in high-energy terms, Cygnus is not calm, it is crowded, active, structurally complicated, massive stars, stellar winds, star-forming regions, remnants, compact objects, extended emission, diffuse plasma, invisible light. It can look graceful. In energetic terms, it's a traffic jam of possible accelerators, which made it exactly the kind of place where the old cosmic ray problem could reappear in a new form. LHAASO and other observatories had identified exceptionally energetic gamma-ray emission associated with the broader Cygnus region. Some of it overlapped with what is known as the Cygnus cocoon, an immense superbubble of hot, turbulent gas surrounding a region of intense star formation. Inside and around that environment lies the Cygnus OB2 association, a massive cluster of young hot stars throwing off strong stellar winds. Even before the newest PEV detections, Cygnus had already been treated as one of the most plausible large-scale particle acceleration zones in the galaxy. The logic was compelling. Fill a region with massive stars, let their winds collide, churn, and inject turbulence into a superbubble, and you have all the ingredients for sustained acceleration on enormous scales. The region did not need help looking guilty. And yet the closer the data were examined, the more another possibility refused to stay in the background. Further along a similar line of sight sat Cygnus X-3. Not a cluster, not a diffuse cocoon, but a compact and far stranger system, an X-ray binary, a tight pairing between a dense compact object, likely a black hole or perhaps a neutron star, and a massive donor star, usually understood to be a Wolf-Rayet star. The donor is no ordinary companion. It is hot, luminous, unstable, and driving off fierce stellar winds. The compact object feeds on that environment, accreting material, reorganizing it through gravity, magnetic fields, and angular momentum into a system capable of launching powerful outflows. This is one of the recurring patterns of the universe. Whenever matter falls inward under extreme conditions, some of it gets flung outward with terrifying efficiency. In binaries like Cygnus X-3, gravity does not simply swallow, it can weaponize. Material spiraling toward the compact object heats up, radiates intensely, and under the right magnetic and rotational conditions, drives jets of plasma outward at high speed. Now the system is no longer merely a bright binary, it is an engine with multiple avenues for particle acceleration, shocks in the jets, interactions between outflows and stellar winds, regions of magnetic dissipation, boundaries where one violently moving flow crashes into another. Theoretically, it was an ideal suspect. Observationally, it was buried in a neighborhood full of other suspects. And this is where timing became decisive in a way direction never could. Because if a signal is truly coming from a compact binary, the binary has one advantage over large diffuse structures: it keeps time. Its geometry changes as the two objects orbit one another. The angle of emission changes. The opacity of surrounding material changes. The compact object moves through the donor star's wind. Depending on how the particles are accelerated and how the gamma rays escape, the system can imprint its orbital motion directly onto the signal. Not a static glow. A periodic fingerprint. That is exactly the kind of evidence astrophysics dreams of in a field built on indirect clues. A single gamma ray points to a direction. A repeating modulation ties the source to a system. Once the signal begins to pulse with the clockwork of an orbit, the interpretation hardens. The source stops being a vague region and becomes an actual engine with a measurable rhythm. And in Cygnus X-3 that rhythm appeared. The key period was about 4.8 hours. Not random variability, not a soft rise and fall spread over some ill-defined interval. A repeating pattern aligned with the orbital timescale of the binary. The gamma-ray signal showed temporal structure that matched the system's dynamics, and when that same timescale connected across other wavelengths, X-ray, infrared, the ambiguity began to collapse. The source was no longer just somewhere in Cygnus. The source was keeping its own appointment. This was a profound shift in the logic of the search. For a century, the field had been battered by evidence that arrived stripped of root and identity. Charged particles bent through magnetic fields. Air showers destroyed the original event. Even directional gamma rays could still leave too many candidates layered along the same line of sight. But periodicity is different. Periodicity is geometry exposed as time. It is the source revealing not merely where it is, but how it moves. And movement is much harder to fake. Once the 4.8-hour modulation was taken seriously, Cygnus X-3 stopped being just one plausible source among many. It became one of the strongest cases that an actual compact galactic system was producing gamma rays in an energy regime severe enough to push directly against the Pevatron threshold, and perhaps beyond it. This is where the phrase most powerful object begins to tilt into something more precise and more unsettling. Because what makes a source extraordinary is not just that it is luminous, or massive, or dramatic invisible imagery. It is that it can solve the acceleration problem under real conditions. It can take charged particles, keep them in an environment where they continue gaining energy, and then let at least some of that energy reappear in a form we can detect. In Cygnus X-3, the combination of compact gravity, extreme stellar wind, orbital motion, and jet physics created exactly the sort of severe environment where nature can do what human language struggles to compress cleanly. Turn a binary system into a particle gun. And the energies involved were not merely high, they were destabilizing. Photons associated with Cygnus X-3 were measured up to several peta-electron volts. That alone would have made the source exceptional. But photons are only the surface accounting. If such gamma rays are being produced through hadronic processes, for example through collisions involving accelerated protons that then generate neutral pions decaying into gamma rays, then the parent protons must carry even more energy than the photons themselves. Not slightly more, several times more. A gamma ray at a few peta-electron volts can imply protons well above that. 10 peta-electron volts and beyond. That matters because it pushes the source into a rarer category. Not simply a Pevatron in the loose sense of generating PV-scale consequences, but potentially what some researchers have described as a kind of super Pevatron, an engine capable of driving hadrons to energies substantially above the canonical threshold that once felt almost theoretical. If true, that means the source is not merely brushing the cosmic ray knee. It is punching through the ceiling that earlier galactic candidates were often only expected to approach under favourable conditions. The implication is easy to state and hard to metabolize. Inside our own galaxy, there may exist compact systems capable of accelerating protons to energies that place them among the most severe natural particle engines we have ever inferred, not in quasars billions of light-years away, not only around supermassive black holes in remote active galaxies. Here, in the Milky Way! And once that possibility is admitted, the emotional structure of the whole story changes again. The question is no longer just whether the galaxy contains Pevatrons. That question has already begun to close. The sharper question is how many different physical architectures can become one under the right conditions. Shock fronts in supernova remnants, pulsar-driven nebulae, stellar wind superbubbles, compact binaries with jets, perhaps, under even harsher circumstances, still stranger regimes. The universe is not using one machine, it is using a family of solutions, and that is why Cygnus X-3 matters so much, not just because it is powerful, not just because it is strange, but because it showed how a source could be identified not merely through energy or direction, but through time, through the internal cadence of the system itself. It was one of the first moments when the hidden machinery of the galaxy stopped looking like a set of abstract possibilities and began to behave like named, measurable engines. The source had not just left debris, it had left a rhythm, but that rhythm carried a deeper complication, because once the evidence begins to separate actual source classes from one another, the old language starts to weaken. Most powerful object is a useful promise at the surface. It gives the mystery a shape the human mind can hold. One object, one champion, one throne of violence at the top of the cosmic hierarchy. Reality is usually less polite than that. The deeper the search went, the less power looked like a single title, and the more it looked like a condition, something that emerges wherever gravity, magnetic fields, turbulence, confinement, and escape combine in exactly the wrong way for our intuition and exactly the right way for acceleration. Which means the real discovery was growing larger than any one source. And colder, because the Milky Way was starting to look less like a collection of stars embedded in emptiness, and more like a distributed machine, a place where under the right conditions, ordinary categories like remnant, pulsar, binary, and nebula become only the visible handles on a deeper reality built from shocks, winds, fields, and violent transfers of energy. The object matters, but the regime matters more. Because once power starts looking like a regime instead of a trophy, the title question begins to dissolve into something more revealing. What is the most powerful object in the universe? At the surface, it sounds like a ranking problem, a hunt for the single greatest beast in the cosmic zoo, the biggest black hole, the brightest explosion, the most energetic source. It flatters a human instinct that wants the universe to arrange itself into clear winners, one object above all others, one definitive answer waiting behind enough data. But the closer high-energy astrophysics gets to reality, the less nature seems interested in those categories. Power, in this part of the universe, is rarely a static property. It is not something an object simply possesses like weight or colour. It is something an environment does. A system channels energy, traps particles, accelerates them, loses some, confines others, releases a fraction, converts motion into turbulence, magnetic order into electric violence, gravity into outflow. What matters is not only what the source is, but what conditions it can sustain. That is why the search kept widening even as individual candidates grew stronger. Supernova remnants still mattered, because shock fronts are among the galaxy's most effective natural acceleration structures. Pulsar wind nebulae mattered, because rotation and magnetism can drive particle energies into brutal territory. Compact binaries mattered, because gravity plus accretion plus jets can turn a small system into a concentrated engine of extraordinary severity. Massive stellar associations and superbubbles mattered, because on large enough scales, overlapping winds and turbulence can create a broader acceleration environment than any single remnant or pulsar alone. None of these source classes simply replaced the others. They complicated them. This is the point where the story stops being about which object wears the crown and starts becoming a confrontation with how the galaxy actually handles energy. And what it reveals is much less comforting than the neat ranking question we began with. The Milky Way does not appear to rely on one privileged machine. It appears to maintain multiple ways of becoming dangerous. That is a very different picture of reality. Because the old visual intuition of our galaxy is so deeply misleading, we grow up under a night sky that feels static because human eyes are tuned to photons in a very narrow range and to timescales close to a lifetime. The stars seem fixed, Constellations look ceremonial. Even when we learn that stars are born and die, collide and collapse, the underlying picture can remain strangely gentle, a huge but orderly system, dynamic in theory and tranquil in experience. High-energy astrophysics tears that picture open. Underneath the visible sky is a non-thermal galaxy, one shaped not primarily by equilibrium, but by departures from it, by shocks, by supersonic outflows, by compact objects spinning down, by magnetic fields storing and releasing energy, by stellar winds colliding, by particles that do not simply sit in a thermal bath, but are driven far beyond it into tails of the energy distribution so extreme that a single proton can arrive at Earth, carrying testimony from an environment no naked eye could ever diagnose. That phrase matters here, non-thermal, because it names the hidden architecture of the problem. A quiet visible sky is usually a thermal picture, light from hot bodies, energy more or less distributed the way ordinary matter tends to distribute it. But cosmic rays belong to a different order. They are matter torn out of that calm description and pushed far above the average. They are signs that the universe does not merely glow, it accelerates. And once you start thinking that way, even the familiar source classes begin to look different. A supernova remnant is no longer just debris from a stellar death. It is a moving pressure discontinuity capable of repeated particle energization. A pulsar is no longer just a rapidly spinning neutron star. It is a machine converting rotational energy into relativistic winds and violent electromagnetic structure. A binary like Cygnus X-3 is no longer just two objects orbiting each other. It is an unstable interface between gravity, wind, accretion, and jet formation. A star-forming region is no longer just a nursery. It is a turbulent field of overlapping winds and shocks, where collective processes may accelerate particles on scales individual objects cannot. The visible labels stay the same. The underlying ontology changes, and that shift matters because the more source classes the search admitted, the harder it became to preserve the comforting simplicity of earlier explanations. For decades, it was tempting to imagine that one dominant mechanism, supernova remnant shocks, perhaps, might largely solve the galactic cosmic ray problem. The appeal was obvious. It reduced the mystery to something physically elegant and astrophysically abundant. Massive stars explode often enough. Their kinetic energy budgets are enormous. The shock acceleration framework is robust. It was, in many ways, the cleanest story available. But the universe has a habit of punishing clean stories when the data get better. As observatories improved, as gamma-ray maps sharpened, as candidate Pevatrons multiplied, the galaxy began to look less like a place with one answer and more like a place with overlapping acceleration ecologies. Different source classes may dominate at different energies, for different particle species, at different evolutionary stages, under different environmental conditions. One source may accelerate electrons with astonishing efficiency and tell you little about the hadronic cosmic rays striking Earth. Another may produce hadrons effectively only during a short early phase. Another may rely on interaction with nearby clouds. Another may require a binary geometry or a dense stellar wind. Another may exist only in rare, transient states. The answer was not shrinking toward a single engine. It was branching. This is where scientific honesty becomes part of the drama, because a weaker script would simplify that branching into false certainty. It would declare the winner too early. It would pretend the mystery is now solved because a few spectacular detections exist and several candidate classes look promising. But the real condition of the field is more severe and more interesting than that. We now know enough to say that PeV-scale particle acceleration is happening in our galaxy. We know enough to identify plausible and in some cases compelling source classes. We know enough to locate regions where the acceleration is real. In a few cases, we can even tie the signal to the timing or structure of a particular system. But knowing that the accelerators exist is not the same as having fully mapped the hierarchy of mechanisms behind them. The search has matured from ignorance into structured uncertainty. That is progress of the most dangerous kind. Because structured uncertainty is what you get when reality has stopped looking simple, but has not yet finished explaining itself. And it was exactly at this stage that the scale of the discovery began to widen again. LHAASO's early detections were stunning enough on their own, enough to establish ultra-high energy gamma-ray astronomy as a more direct road into the Pevatron problem than many had dared hope. But the first dozen candidate sources were never going to be the end of the story. They were proof of concept. They were the first tears in the old fabric. Once the instrument kept watching, and once other observatories around the world began comparing, extending, and cross-checking the data, the candidate population expanded. What had initially looked like a handful of extraordinary exceptions began to feel more like the exposed edge of a larger hidden population. Catalogues of galactic ultra-high-energy gamma-ray sources grew. Candidate Pevatrons multiplied. Some were compact, some extended, some associated with known remnants or pulsars, some embedded in more complex regions, some more easily interpreted than others, some almost certainly mixed in origin. The point was not that every source was understood. The point was that the Milky Way was no longer defensibly describable as a mostly placid stellar system, punctuated only occasionally by energetic oddities. The energetic oddities were becoming part of the system's basic description. That realization lands with unusual force because of how ordinary the galaxy looks from inside it. Human beings have always been vulnerable to scale as a form of false reassurance. What is large enough can feel stable simply because we cannot perceive its activity directly. A mountain seems motionless though it is eroding. A continent seems fixed though it drifts. A galaxy seems peaceful though it is threaded with shocks, compact remnants, particle winds, and acceleration sites capable of hurling matter to energies that make our best machines look provincial. The Milky Way was never serene. It only looked that way at human wavelengths. And that line is more than rhetoric. It is a statement about epistemology, about what kind of creatures we are, and how badly our default senses misdescribe the physical world. The visible sky is a filtered interface. It is not a complete account. It hides magnetic fields because we cannot see them. It hides ionization because we do not feel it until it becomes pathology or instrument failure. It hides relativistic particles because they do not paint tracks across the air for our benefit. It hides non-thermal processes because our perception evolved for survival on a planetary surface, not for diagnosing a galaxy's hidden energy economy. Cosmic rays exposed that mismatch early. Pevatrons made it impossible to ignore. Because once you know that our galaxy contains environments capable of accelerating particles into the peta-electron-volt range, the visible Milky Way acquires a second identity. The luminous band above us remains real. So do the nebulae, clusters, and familiar constellations. But beneath them is another map, a harsher cartography of shocks, winds, compact objects, stellar associations, and high-energy leakage. A map not of what shines prettily, but of where matter is being driven toward its limits. This is the midpoint where the opening illusion is gone for good. The sky no longer looks silent in the same way. Not because every star hides a catastrophe, because the galaxy as a whole is more physically active than the visible image ever implied. And that changes the meaning of the particles reaching Earth. They are no longer just mysterious projectiles from unknown causes. They become local consequences of a general truth. We live inside a system whose hidden machinery is constantly redistributing energy in ways that exceed intuition. What still remains is to understand how far that truth reaches. Because once the Milky Way stops looking like a calm container of stars, another question starts pressing forward. If so many different environments can accelerate particles this violently, then perhaps the real threshold is not the object at all. Perhaps it is the mechanism. And if that is true, then the next thing we have to understand is what all these candidate engines are actually doing in common when they become extreme. Because once you strip away the names, remnant, pulsar, binary, cocoon, the same deeper question keeps returning in different clothes. How does the universe actually accelerate a particle? Not metaphorically. Not in the broad popular science sense where powerful means luminous or catastrophic. In literal physical terms, what has to happen for an ordinary charged particle, a proton, an electron, a nucleus, to gain energy over and over again until it enters a regime so extreme that its presence can still be detected light years away as gamma rays, or much later as cosmic ray fallout in our atmosphere? This is the point where the story has to earn its authority. Because without mechanism, ore is cheap. And the mechanisms, once you see them clearly, are severe enough on their own. The first thing to understand is that nature almost never accelerates particles by a single clean shove. The energies involved are too high, the loss is too severe, the The scale's too large. Instead, the universe relies on environments where particles can remain trapped inside organized violence long enough to be pushed repeatedly. Acceleration is usually a confinement problem before it becomes an energy problem. A particle gains energy only if it stays inside the machine. That simple statement sits under almost everything in this field. Take a shock front. It is one of the most efficient natural acceleration structures we know. A shock is not just a moving boundary. It is a place where the physical conditions on one side differ abruptly from the conditions on the other. Velocity, density, magnetic structure, pressure. In an ordinary collision, we imagine particles smashing into one another directly. But in the tenuous plasmas of astrophysics, many shocks are collisionless. The particles do not need to hit like billiard balls. Electromagnetic fields do the work, scattering particles across the front and reorganizing the flow. Now imagine a charged particle near such a shock. If magnetic irregularities on either side scatter it back and forth across the boundary, then every crossing can increase its energy. The particle samples converging flows. It steals a little ordered motion each time. No single crossing is miraculous. The miracle is repetition. Stay inside that environment long enough, and the gain compounds. This is diffusive shock acceleration, the same mechanism that made supernova remnants so compelling and still underpins a huge fraction of high-energy astrophysics. The violence is not in one event. It is in being denied escape. This is why magnetic fields matter so much, not because they merely decorate the environment, but because they decide whether a particle remains in the game. A field can bend a trajectory, scatter it, trap it, redirect it toward another crossing. Too weak, and the particle escapes before gaining much. Too ordered in the wrong way, and it may be guided out. Turbulent enough, strong enough, structured enough, and confinement improves. The source becomes more efficient. The same basic shock can be trivial or extraordinary depending on whether the surrounding magnetic architecture lets particles stay long enough to climb. That is the hidden cruelty of particle acceleration in space. The source must energize and imprison at the same time, and shock fronts are only one answer. Pulsar environments solve the problem differently. There, the energy reservoir is not primarily the bulk kinetic flow of ejecta crashing into the interstellar medium, but the rotational energy and magnetic structure of a compact object. A pulsar is born spinning rapidly. Its magnetic field is immense. Rotation winds up the surrounding electromagnetic environment into something almost too extreme to describe cleanly without losing the body feel of it. Space near the pulsar is no longer passive background. It becomes an electrodynamic machine. Particles are extracted, pair cascades form, plasma is launched outward, and the wind carries away energy at relativistic speed. But again, launching particles is not enough. The problem is how to keep pushing them. That is where the pulsar wind termination shock matters, because the wind does not expand forever into emptiness. It encounters surrounding material, it is forced to decelerate, the outflow reorganizes, energy piles up at the boundary between the freely streaming wind and the slower external medium. The result is another acceleration site, one in which relativistic plasma, magnetic turbulence, and shock structure combine in ways we still do not completely understand. Some of the highest energy electrons ever inferred in our galaxy almost certainly come from regions like this, which is why the Crab mattered so much. Not because it answered every question, but because it proved the universe can force electrons into an energy regime where even their rapid radiative losses do not stop the climb fast enough. That phrase radiative losses is easy to gloss over. It should not be, because every accelerator in the universe is fighting leakage. Electrons, especially, are difficult to accelerate to extreme energies because they are so quick to betray the process that created them. Put them in a magnetic field, and they radiate synchrotron emission. Let them scatter ambient photons and they lose energy through inverse Compton processes. The faster they go, the worse the problem becomes. Their brilliance is the price of their fragility. An electron accelerator capable of reaching the Pev regime must push so efficiently that acceleration outruns loss, at least briefly. That is not merely impressive. It is physically unforgiving. Protons and heavier nuclei are different. Because they are more massive, they do not radiate away energy as readily under the same conditions. In one sense, that makes them better long-range couriers of violence. They can survive the journey through the galaxy more effectively, but their very durability creates another challenge, proving that a given source accelerated them. Electrons advertise themselves with bright radiation. Protons are often more indirect. To catch them in the act, astronomers usually need to see the consequences of their interactions, collisions with gas that generate pions, which then decay into gamma rays, or neutrinos in more extreme contexts, or some other hadronic signature that can be traced back with enough confidence. So the field's hardest problem sits right at this divide. The galaxy clearly accelerates electrons. Does it accelerate hadrons, and where? That question forces a different level of scrutiny on every candidate source. A bright gamma-ray region may be leptonic, dominated by electron processes. Another may be hadronic. Some may be mixed. A given object might look like a spectacular Pevatron, and still fail to explain the majority of the cosmic rays arriving at Earth if its acceleration channel favours the wrong particles or the wrong timescale. Which is why environment matters more than labels. A supernova remnant can become a hadronic accelerator if its shock and magnetic conditions are favourable, and if the age is right. But it may only reach its highest energies in a brief early phase. A pulsar wind nebula can produce astonishing gamma-ray emission through electrons, yet remain ambiguous as a source of galactic hadrons. A molecular cloud near a remnant can glow in gamma rays not because it is doing the acceleration itself, but because previously accelerated protons escaped the remnant and later collided with dense gas there. A compact binary may produce intense gamma rays through jets and wind collisions, but the precise mix of leptonic and hadronic processes can still be difficult to untangle. Every source class is really a bundle of timescales, geometries, losses, and escape routes. And escape is the last part of the mechanism that matters. Because an accelerator that never lets particles out does not explain cosmic rays at Earth. At some point, the particle has to leave the machine, but it has to leave at the right moment, too early, and it never reaches the highest energies, too late, and it may lose energy inside the source or remain trapped until the conditions change. The most effective cosmic ray engines therefore solve a brutal balancing act. Confine long enough to accelerate, release early enough to export. The universe does not merely have to make energetic particles. It has to let them go. Once you start viewing the field through that lens, the apparent diversity of candidate sources becomes easier to understand. What they share is not a superficial identity, but a set of structural requirements, an energy reservoir, a mechanism for transfer, magnetic conditions for confinement, a path for escape, and some way for the accelerated particles to reveal themselves afterward, whether by colliding with matter, upscattering photons, radiating in magnetic fields, or eventually striking Earth after a journey long enough to erase their point of origin. That is the hidden architecture beneath the source catalogue. It is also why the phrase most powerful object becomes subtly misleading as the science gets better. It suggests that power lives inside the object like a possession. In reality, what matters is whether the object can sustain a process. A black hole, a neutron star, a remnant shell, a stellar cluster. None of them matters in isolation from the flows, fields, and interfaces surrounding them. The object is often just the anchor point where the relevant conditions gather. The acceleration itself happens in the structure around it. Power here is not a noun. It is a behavior, and that shift matters because it prepares the ground for the part of the story where even our best candidate classes begin to blur. Once you know the universe can use shocks, winds, turbulence, rotation, magnetic reconnection, and jets as different ways of solving the same acceleration problem, then the category boundaries soften. A supernova remnant can feed a molecular cloud, a pulsar can live inside a remnant, a binary can sit in a crowded star-forming region. A compact object can inherit and reshape the debris of earlier violence. What we call one source may actually be a chain of linked environments, passing energy forward from one structure into another. The galaxy is not composed of isolated engines. It is composed of coupled systems. That is why the most important remaining question was never just which objects were brightest, nearest, or easiest to name. The deeper question was which of these systems were actually crossing the threshold into hadronic PEV acceleration in a way robust enough to explain the invisible bombardment that first started this descent. And that question kept pulling the search toward the same painful distinction. Seeing gamma rays is not enough. You have to understand what kind of particle paid for them. Because the sky above Earth is not being filled by elegant theoretical categories. It is being struck by mostly protons and nuclei. If the source can only accelerate electrons, it proves something profound about the universe. But it does not yet solve the original injury in the opening image. The real engines we need are the ones that can do the harder thing. Accelerate hadrons to the point where some fraction escape, cross interstellar space, and eventually reach our atmosphere as the damaged survivors of a much larger event. That stricter standard is what turned some triumphs into partial answers. And it is what made a few systems in particular feel less like beautiful curiosities and more like the first serious confessions. Because by this point, the galaxy had already admitted that it could build particle accelerators more powerful than ours. What it still had to admit was which of them were firing the bullets. That is the point where a field stops being impressed by extremity alone. A source can be violent, bright, famous, the site of extraordinary electron acceleration. It can produce gamma rays so energetic that they already force a rewrite of the old picture of the Milky Way. And still, under the stricter logic of the original question, it may only count as a partial answer. Because the particles raining through our atmosphere are not a philosophical category. They are mostly hadrons. Protons, atomic nuclei, massive enough to survive the journey better than electrons, stubborn enough to reach us after the galaxy has bent, scattered, and partially erased their route. If the goal is to explain the hidden bombardment above Earth, not just to admire nature's accelerators in the abstract, then the most important sources are the ones capable of doing the harder, colder thing, accelerating hadrons to the peta-electron-volt scale and beyond. That is where the search for cosmic ray origins becomes a process of elimination. The Crab Nebula, for all its severity, sharpened this distinction rather than erasing it. It proved that the Milky Way contains environments capable of electron acceleration at energies so high that the usual language of extreme starts to lose specificity. But electrons are not enough. They radiate too efficiently, advertise their presence too brightly, and die too quickly to explain the bulk of the particles still reaching Earth after long galactic journeys. An electronic Pevatron is a triumph. A hadronic one is a confession. That difference forced astrophysicists to look at candidate sources with a much harsher eye. A supernova remnant, for example, remains one of the strongest broad candidates because it naturally creates shocks, and shocks are one of the few mechanisms we know that can energize hadrons efficiently over large regions. The energy reservoir is immense. A single core collapse supernova releases kinetic energy on a scale almost indecent by human standards. If even a modest fraction of that energy goes into accelerated particles, then remnants could contribute a major share of the galaxy's cosmic rays. That argument has never gone away, because in a deep sense it is too physically plausible to discard casually. But physical plausibility is not the same thing as observational closure. As the field pushed closer to the knee, the difficulty became sharper. The models often suggested that a remnant's best chance to reach true PeV hadronic energies comes very early, when the shock is fastest, the magnetic amplification strongest, and the environment most favourable for confinement. That may last only decades to perhaps a century at the most optimistic end in many scenarios. After that, the remnant continues to accelerate particles, but the ceiling begins to fall. The system is still violent. It may still shine in gamma rays. It may still dominate part of the cosmic ray budget. Yet the brief interval when it acts as a true proton Pevatron may already be over by the time we study it clearly. Which means the source class most likely to matter may also be the one easiest to miss in its most important phase. That is a recurring cruelty in this field. Nature does not merely make the evidence indirect, it often makes the most decisive state of a source transient. Still, there are ways the signature can survive, even if a remnant itself is no longer accelerating hadrons all the way to the top of the PeV range. Particles accelerated earlier may already have escaped into the surrounding medium. If those protons wander into nearby dense molecular clouds, they can collide with gas there and produce gamma rays. In that case, the cloud glows not because it is the engine, but because it is catching the exhaust. The source and the visible consequence separate. The culprit may be fading, the evidence can remain. This is a subtle but devastatingly important idea. Sometimes what astronomers detect is not the machine itself. It is where the machine's escaped particles finally hit something thick enough to light up. That possibility preserved supernova remnants as serious contenders even when direct proof of ongoing hadronic PeV acceleration remained difficult. It also reinforced the larger lesson that the galaxy's acceleration architecture is distributed. Energy is injected in one place, transported through magnetic structure, and revealed somewhere else. A source may therefore look less like a self-contained object, and more like a relationship between a compact accelerator and the environment it contaminates. Pulsars complicated the picture in a different way. Their credentials as electron accelerators were already formidable. Their winds, shocks, and magnetized nebulae naturally produce severe non-thermal emission. Several candidate Pevatron regions line up well with pulsar systems or pulsar wind nebulae. In some cases, they may dominate the observed gamma-ray signal. Yet here too the hadronic question remains the dividing line. A pulsar can flood its surroundings with electrons and positrons, creating gamma rays through leptonic processes that are spectacular and real, while still telling us less than we need to know about the proton component that ultimately concerns the cosmic ray problem. So every time the field thought it had found a likely answer, the same deeper demand returned. What particle is actually being accelerated? And because that question is not always easy to answer cleanly from gamma rays alone, astronomers began to look for source properties that could break the ambiguity indirectly. Morphology could help. A glow aligned with a dense cloud might hint at hadronic interactions. A nebular geometry close to a pulsar might suggest a leptonic origin. The spectral shape could help. Time variability could help. Multi-wavelength comparisons could help. If the gamma rays rise and fall with a binary orbit, for example, that points strongly toward a compact system rather than a large diffuse cloud. If the source is extended over a large region of star formation, that suggests something else again. But none of these are magical solutions. They are pieces of a case, and the more carefully the evidence was assembled, the less the galaxy resembled a place with one clean source class and one clean explanation. It started to look like a hierarchy of partial truths. Supernova remnants likely matter enormously. Pulsars almost certainly matter. Molecular clouds can function as illuminated targets. Stellar clusters and superbubbles may sustain larger-scale acceleration. Compact binaries may do things more severe than many astronomers had once expected. Different systems may dominate under different conditions, for different particle species, and at different energies. This branching is not a failure of the science. It is what science looks like when the object of study is real enough to break simplifications. And yet even inside that branching field, some sources began to feel qualitatively more dangerous than the rest, not merely because they fit one preferred theoretical narrative, but because their observational behavior implied a direct crossing of the threshold that had haunted the field for so long. Cygnus X-3 was one of those sources. Its importance was not just that it emitted at extreme energies. The Milky Way contains many energetic places. Its importance was that the system offered multiple lines of seriousness at once. It was compact. It was violent. It was structured by a short orbital period. It contained a dense stellar wind from a massive companion and an accreting compact object capable of launching jets. It kept time in its own emission, and the gamma rays associated with it reached energies so high that, if they arose from hadronic processes, the parent protons had to be driven into a domain well above the nominal PV scale. This is where the vocabulary begins to strain. A source that can accelerate protons to around 10 peta-electron volts or more is not just very powerful. It is operating in a domain where the old psychological threshold, the one that made the knee seem like a distant boundary, begins to lose its function as a ceiling. The source is no longer approaching the line, it is crossing through it. That is why some researchers have reached for phrases like super Pevatron, not to inflate the source artificially, but to signal that the usual category may already be too small. And the moment the possibility enters the story, the original title question bends again. Most powerful object in the universe sounds singular and theatrical, but the deeper truth is more disturbing. The sources that matter most here are not necessarily the largest or most luminous objects known. They are the systems whose specific conditions solve the acceleration problem under brutal constraints. A compact binary can outperform a grander-looking structure if its geometry, outflows, confinement, and interaction region are harsher in the right way. A remnant may be more important at one phase, a pulsar at another, a stellar association at another. In other words, what matters is not grandeur in the visual sense. It is efficiency under extremity. That idea also helps explain why black holes began re-entering the conversation in a more serious way. For years, the notion that particles colliding near a black hole could reach enormous energies had lived partly in the territory between provocative theory and astrophysical practicality. The famous Barnard-Silk West effect suggested that, near the horizon of a rapidly spinning black hole, collisions could in principle achieve enormous centre of mass energies under special conditions. The early objection was immediate and sensible. Even if the energies were huge, why expect the resulting particles to escape rather than disappear into the black hole? That criticism never fully killed the idea, but it kept it from becoming a comfortable explanation. Then the conversation matured. More recent work suggested that not all particles produced near such extreme gravitational environments would necessarily be lost. Some fraction could escape under the right circumstances, especially in more realistic astrophysical settings involving accretion flows, magnetic fields, and outflows. At that point, the black hole scenario stopped feeling like a decorative thought experiment and started sounding more like part of a larger pattern we had already seen elsewhere in the galaxy. Violent confinement, severe gradients, repeated energization, and selective escape. The object changes. The logic remains. That is the key to this whole stage of the story. Once you understand the acceleration problem correctly, different source classes begin to look like different answers to the same underlying demand. They all need a reservoir of energy. They all need a mechanism of transfer. They all need a geometry of confinement. They all need a path of release. And they all need to leave behind evidence we can still read after the universe has bent, delayed, diluted, or broken most of it. So the question what founds the cosmic rays is no longer really asking for one object. It is asking which environments in the Milky Way are physically ruthless enough to turn matter into a galactic export. And by this point, the answer was no longer hypothetical. The candidate population was growing. The classes were multiplying. The old peaceful galaxy was gone. What remained was to understand what all of these detections were doing to the larger picture of the Milky Way itself. Because once enough severe sources exist, the discovery stops being about isolated engines and starts becoming about the kind of galaxy we actually live in. Because isolated engines are one kind of discovery. A changed galaxy is another. Finding one spectacular source is exciting. It gives the mind something to hold, a name, a location, a system dramatic enough to anchor the story. But once the detections begin to accumulate, once candidate Pevatrons stop looking like rare curiosities and start appearing across different regions and source classes, the meaning shifts. The question is no longer just what these objects are. It becomes what kind of Milky Way produces them so readily. That is a more destabilizing question, because it reaches past astrophysical bookkeeping and touches the way human beings instinctively imagine their home galaxy. Most people carry some version of the same visual model, a luminous spiral of stars, gas, and dust, rotating in the dark with a kind of stately grandeur. There may be violent events inside it, supernovae, collapsing stars, compact binaries, but they feel like exceptions. Local disruptions inside a larger picture of order. High-energy astronomy does not quite permit that comfort. Once dozens of ultra-high-energy gamma-ray sources begin to populate the galactic map, the Milky Way stops looking like a mostly calm structure punctuated by occasional extremes. It starts to look like a system whose hidden baseline includes repeated, distributed, non-thermal violence. Not everywhere equally, not at every moment, but often enough, and in enough different physical settings, that the violent picture can no longer be treated as a footnote to the visible one. This is one of the deepest reversals in the whole story. The visible galaxy is made of light. The operative galaxy is made of transfer. That line matters because it reframes what counts as fundamental. We tend to privilege what we can see directly: stars, nebulae, clusters, dust lanes, the soft river of the Milky Way across a dark sky. But the processes shaping cosmic rays belong to another order. They are not primarily about surfaces glowing at some equilibrium temperature. They are about energy being pushed out of equilibrium, concentrated, redirected, trapped, and released. A galaxy rich in cosmic accelerators is not merely luminous. It is dynamically stressed in ways that visible light only partially reveals. This is what the expanding catalogues began to force astronomers to confront. LHAASO's early source lists were already enough to make the older picture wobble. But as more data accumulated, and as complementary observatories added their own detections across overlapping energy ranges, the pattern became harder to dismiss as a set of anomalies. Candidate galactic Pevatrons multiplied. Some were associated with known remnants, some with pulsars or pulsar wind nebulum, some with complex star-forming regions, some with compact systems. Some remained ambiguous, but ambiguity itself was part of the point. The unresolved cases did not weaken the conclusion that the galaxy was energetically harsher than expected. They strengthened it, because they implied that the hidden acceleration landscape was broader than any one favoured source class. The galaxy was not offering one answer. It was exposing a population, and populations change ontology. A single object can be extraordinary without forcing a rewrite of the wider system. A population does not let you do that. Once enough examples exist, the trait stops being exceptional and starts becoming diagnostic. It tells you something about the environment that produced them, not a fluke, not a singular marvel, a recurring solution to a recurring physical problem. The Milky Way, in other words, appears to be better at building particle accelerators than older intuition allowed. That sentence is almost absurdly simple compared to what it means, because hidden inside it is a new image of our cosmic home, not a passive stellar city lit from within, but a structure threaded with shocks, compact remnants, colliding winds, magnetized outflows, and regions where matter is repeatedly driven toward limits that only become visible through the hardest photons and the rarest particle debris. A galaxy like that feels different to live inside, even if nothing in daily life changes. That is the eerie part. Most of this hidden energetic structure never becomes part of human experience in the direct sensory sense. The constellations do not redraw themselves to warn us. The sky does not flicker with labels marking regions of ultra-high energy acceleration. Your body does not feel the galactic magnetic topology through your skin. The atmosphere absorbs the worst of the incoming punishment and turns it into silent showers. Satellites and detectors notice what ordinary perception cannot. Physics is busy where sensation remains calm. So the emotional effect of this discovery is not fear in the cinematic sense. It is estrangement. The realization that the world you inhabit sits inside a larger machine whose most consequential behaviors are almost completely invisible at human scale. And that estrangement becomes stronger when you remember how long cosmic rays were already telling us this without our knowing how to read them. For more than a century, the evidence was reaching Earth. The atmosphere was already being ionized, instruments were already being perturbed, the galaxy was already exporting energetic residues of its hidden processes into our local environment. The main thing that changed was not the underlying reality. It was our interpretive power. That is another reason this story matters beyond the narrow borders of astrophysics. It is a case study in how reality can be active, consequential, and completely misdescribed by ordinary intuition for generations. The stars looked calm, the galaxy looked decorative, space looked empty enough to separate there from here. Then better instruments, larger detectors, and more disciplined theory revealed that our planet lives under a constant drizzle of evidence from violent processes unfolding elsewhere in the Milky Way. The sky did not become more dangerous because we discovered Pevatrons. It became less falsely innocent. That distinction is the grown-up version of the opening fracture, and it also helps explain why the title question becomes more complicated the longer you sit with it. The most powerful object in the universe is a good doorway, but it invites the wrong final image if taken too literally. It suggests that somewhere there is a cosmic champion, one supreme thing standing alone above all rivals. But high-energy astrophysics keeps pushing in the opposite direction. It suggests that power is contextual, process-driven, and distributed across multiple architectures. A pulsar may dominate one regime, a young remnant another, a compact binary another, an active black hole environment another. Massive stellar associations may create collective acceleration zones that no single object could sustain in isolation. The deeper truth is less theatrical and more severe. The universe does not only build powerful things, it builds conditions under which power becomes transmissible. That is what cosmic rays really reveal. They are not a census of glorious objects. They are evidence that the cosmos repeatedly solves the problem of transferring enormous amounts of energy into tiny particles and then, crucially, allowing some of those particles or their signatures to escape. The escape matters as much as the acceleration, because an unseen engine sealed perfectly inside itself would not rewrite our picture of the galaxy. What rewrites the picture is leakage. The fact that these processes do not remain local. They contaminate the larger medium. They propagate outward. They become part of interstellar ecology. That word ecology may sound too soft for what is happening, but it is exactly right if used carefully. Not ecology in the biological sense, ecology in the structural sense. Multiple environments interacting, feeding one another, shaping the conditions under which later processes occur. A supernova produces a remnant. A remnant may shelter a pulsar. Escaping particles may seed nearby clouds. Stellar associations stir turbulence in surrounding gas. Compact objects feed on winds and then return jets into their environment. One burst of violence becomes the medium for another. The galaxy is not a set of isolated laboratories, it is a chain of consequences. And once you begin to see it like that, the Milky Way starts to feel less like scenery and more like weather. Not weather on human timescales, of course, not storms we watch roll in over an afternoon, but a larger kind of weather. Fields, winds, shocks, outflows, compressions, releases, a galaxy with an energy climate, a hidden circulation of violence, most of it too large, too sparse, too slow, or too non-thermal for the senses that evolved inside one small biosphere, yet real enough that, every so often, some fragment of that circulation falls through our atmosphere and reminds us that we're not standing outside it. We are downstream. That is the real shift in perception this stage of the story delivers. Cosmic rays are no longer just mysterious projectiles, and Pevatrons are no longer just named curiosities. Together they reveal the Milky Way as an active, coupled system whose invisible processes are still reaching into local space. The galaxy is not only above us, it is arriving. And once that becomes visible, another pressure begins to build. Because if what reaches Earth is only the leakage, only the damaged aftermath of larger processes elsewhere, then the particles we detect are not the event itself. They are the residue. Which means the ending of this story cannot really live out in the source regions alone. It has to come back here, to the atmosphere, to the planet, to the fact that what first looked like a distant cosmic mystery was always, in a diluted form, already happening over our heads. What reaches us is not the engine. It is what the engine sheds. Which is why the final turn of the story is not outward, towards some ever more exotic object, but downward, back through the atmosphere, back to the planet, back to the opening mistake. Because the most important thing about cosmic rays was never that they proved the universe could build extreme accelerators. It was that those accelerators were never fully remote. Their products, or at least their surviving signatures, reach us. Not dramatically enough to satisfy instinct, not in visible beams or cinematic impacts, in a way that is far more unsettling than spectacle, continuously, silently, and for the most part unnoticed. A primary cosmic ray hits the upper atmosphere and the atmosphere answers by destroying it. That destruction is also a translation. One incoming particle becomes a many-bodied event, a shower of secondaries spreading through the air, some dying quickly, some reaching the ground, some punching through rock, buildings, detectors, even us. Muons pass through matter with an indifference that makes them feel almost abstract until you remember they are here because somewhere else. Some engine accelerated a parent particle to absurd energies and then let it go. What reaches Earth is not the thing itself. It is the argument after impact. That is the right emotional register for the ending, because by now the story has changed scale several times. It began with the visible illusion of peace. It sank into a century-long forensic problem. It widened into the discovery of Pevatrons, then narrowed again into mechanism, then widened once more into a rewritten picture of the Milky Way. All of that matters, but none of it fully lands unless the viewer feels the return, unless the galaxy's hidden machinery is brought back into the ordinary frame where the mistake first lived. The sky above Earth still looks quiet. That has not changed. What has changed is what that quiet means. It no longer means safety, distance, or passivity. It means that human perception is tuned to the wrong channels for most of reality's important work. The stars are still there, scattered in apparent stillness. The dark between them still looks empty, but now the emptiness has been stripped of innocence. We know it is threaded with fields. We know those fields redirect charged particles long before they reach us. We know compact objects, shocks, winds, and jets are continuously redistributing energy across the galaxy. We know some of that energy is being forced into single particles at scales our technology can barely imitate. And we know that what falls through the atmosphere is the surviving residue of that hidden labour. The old comfort is gone. Not because the universe became more violent while we were looking, because it was always violent enough to leave marks, and only now are we learning how to read them. That distinction carries a deeper philosophical weight than the title seems to promise. People often imagine that science makes reality feel cleaner, that explanation reduces strangeness by replacing mystery with mechanism. Sometimes it does. But in fields like this, mechanism deepens the strangeness. The more precisely we understand what must be happening, the less the visible world feels like a complete account. The stars become interfaces, nebulae become consequence fields, binaries become energy conversion systems, supernova remnants become transient laboratories of confinement and escape. Even the atmosphere becomes part of the story, not as a passive shield, but as the final medium that tears incoming evidence apart and spreads it over the planet. Knowledge here does not restore the original world. It removes it. This is why the phrase most powerful object in the universe ends up being both useful and insufficient. Useful because it gives the mind a way into the problem. Insufficient because the real discovery is not that one thing somewhere is stronger than all the rest. The real discovery is that the cosmos has multiple ways of becoming severe, and that power in this domain is not a title, but a transfer function. Under the right conditions, ordinary categories of object become less important than the processes they sustain. A remnant, a pulsar, a binary, a black hole environment, a stellar association. Each can become a site where energy is trapped, intensified, and flung outward in particulate form. The object matters, but the regime matters more, and the regime is what reaches us. That line is worth sitting with, because it sharpens the meaning of everything that came before. Victor Hess did not merely discover strange ionization at altitude. He discovered that Earth is not radiatively self-contained. LHAASO did not merely detect record-breaking photons. It exposed a hidden class of galactic environments that had moved through theory for decades without being nailed down observationally. The Crab Nebula did not merely look spectacular in gamma rays. It proved that electron acceleration in our galaxy can outrun losses far enough to touch the PV scale. Cygnus X-3 did not merely produce an extraordinary signal. It showed that, under the right compact conditions, a system can timestamp its own violence and imply hadronic energies that punch straight through older ceilings. Each discovery narrowed the technical mystery. Together they widened the ontological one. What kind of reality are we actually living in? If a calm night above a sleeping city can be full of invisible evidence from natural particle accelerators distributed across the Milky Way, that is not a rhetorical flourish. It is the real, matured form of the opening question. The naive version asked what powerful object could possibly produce such energies. The grown-up version asks what sort of universe makes such production normal enough that its residue reaches Earth constantly, and yet hides the whole arrangement behind a sky our senses still interpret as tranquil. The answer is not comforting, but it is beautiful in a harder way than comfort allows. We live in a lawful universe that is under no obligation to feel intuitive at human scale. Its deepest processes often do not announce themselves in forms we are built to notice. They arrive as background, as ionization, as statistical anomalies, as broken particle showers, as subtle damage in electronics, as photons with impossible energies, as patterns in spectra, as timing signatures repeating every few hours in a distant binary system. Meaning arrives in fragments, and understanding means learning how to assemble those fragments into a world picture more severe than the one sensation offered first. That is what happened here. The sky did not lose its beauty. It lost its simplicity. And perhaps that is the strongest kind of scientific transformation, not replacing wonder with mastery, but refining wonder until it becomes structurally true. The stars remain beautiful, but beauty is no longer the whole story. The dark remains immense, but emptiness is no longer what it seems. Even the idea of space becomes less like a container, and more like a medium full of fields, background light, hidden trajectories, and active regions where matter is repeatedly pushed beyond the comfortable terms of equilibrium. We began with a visual illusion. We end with a different kind of sight. Not literal vision, something harsher. The ability to look at the same night sky and know that behind the visible constellations is another map entirely, one drawn in shock fronts, pulsar winds, molecular clouds, compact binaries, and gamma rays so energetic they can only have come from environments already close to the limits of what galactic matter can do. And above all, the ability to understand one last inversion. The particles that strike our atmosphere are not the main event. They are what escapes the main event. They are the overspill from processes larger, more violent, and more structurally fundamental than the fleeting shower we measure on Earth. They are not the engine, not the wound, not even the full projectile. They are the surviving fragments of a transfer that began somewhere else, under conditions our species has only recently become capable of naming, which means that every cosmic ray detected above or around this planet carries the same quiet implication. The Milky Way is still working, still accelerating, still shedding evidence of hidden violence into the dark, and when that evidence falls through our atmosphere, it does not arrive as a warning. It arrives as a reminder: the night sky is not peaceful. It only ever looked that way, and that is still not the farthest consequence of the discovery. Because once you accept that the night sky was misread not just emotionally but physically, another illusion starts to fail with it, the illusion that explanation makes the universe feel smaller. Usually, when a mystery is solved, it contracts. The unknown becomes known. The frightening thing gets a name, a mechanism, a place in the system. It stops feeling metaphysical and starts feeling technical. In many parts of science, that is exactly the right emotional arc. Lightning becomes charge separation, disease becomes pathogens, planetary motion becomes gravity. The world grows more intelligible and, in a certain sense, more domesticated. High-energy astrophysics often moves the other way, because here, the mechanism does not reduce the scale of the thing, it enlarges it. To say that cosmic rays come from natural particle accelerators inside the Milky Way is not to tame the mystery. It is to discover that the familiar galaxy has a second anatomy beneath the visible one, an anatomy made not of objects alone, but of thresholds, losses, fields, traps, and release channels. Every answer enlarges the system around it. A PV photon does not simply explain itself by pointing to a source. It forces you to imagine the source's environment. The environment forces you to imagine the confinement. Confinement forces you to imagine the surrounding magnetic topology. That topology forces you to think of the galaxy not as a star map, but as an active medium, and the moment you do that, the whole visual language of calm breaks apart. The visible sky was only ever the skin of the event. That is why these discoveries feel less like filling in gaps and more like cutting through a false floor. The old cosmos remains, but it loses authority. Stars are still stars, nebulae still glow, the Milky Way still arches overhead in pale light. But once you know that the same galaxy contains dozens of candidate Pevatrons and a growing number of systems pushing toward or beyond the energies once treated as theoretical boundaries, the visible image becomes something almost deceptive in its incompleteness. It is not wrong, it is simply too shallow. And shallow descriptions can be more dangerous than false ones, because they let intuition keep operating after it should have surrendered. This is where the phrase most powerful object finally breaks under its own weight. Not because there are no extraordinary objects. There are. Some are so extreme that the word object barely contains them. A compact binary feeding a jet through a dense Wolf-Rayet wind. A pulsar winding space around itself into a relativistic outflow. A young remnant using a shock to steal energy from its own expansion. Even certain black hole environments, under the right conditions, may become acceleration sites far harsher than older caution once allowed. But the deeper lesson is that power in the universe is not rank the way spectacle would rank it. The strongest engine is not always the largest thing. The most consequential source is not always the brightest one. And the most revealing discovery is not the source alone, but the fact that the cosmos keeps finding ways to solve the same problem, how to push matter upward through an energy ladder without losing too much of it too soon. That repetition is what makes the story feel colder than a simple hunt for a record holder. A single monster can be admired. A recurring mechanism has to be lived with. If the universe had produced only one astonishing accelerator somewhere far away, the discovery would be grand, but containable. Once it becomes clear that multiple source classes, under multiple conditions, can enter this regime, the meaning changes. The regime itself becomes part of reality's baseline. Not universal everywhere, not common in the casual sense, but common enough that our home galaxy is shot through with environments capable of acts of acceleration our species still treats as near miraculous. The miracle, of course, is only what lawful behavior looks like when it outruns intuition. That may be the most important philosophical residue of the whole descent. Human beings do not struggle with cosmic rays because they are supernatural. We struggle with them because they are natural in a universe whose natural scales and processes were never built to be emotionally comfortable. The laws are not chaotic. They are not breaking. There is no conspiracy hidden in the data, no need for theatrical rebellion against physics. What makes the story unsettling is almost the opposite. Everything works too well. Magnetic fields bend charged particles exactly as they should. Shock fronts accelerate them exactly as violent plasmas allow. Gamma rays interact with background photons exactly as quantum electrodynamics predicts. The atmosphere destroys primaries and generates showers exactly because matter behaves lawfully under collision. Reality is not strange because it is lawless. Reality is strange because the laws are perfectly capable of producing worlds no intuition would invent on its own. That is what the viewer is meant to feel by now, not confusion, but estrangement with structure, a controlled discomfort, the sense that the universe has become more coherent and less familiar at the same time. The Milky Way is no longer a distant luminous setting for human stories. It is a distributed energy system, and Earth exists inside its leakage field. Our atmosphere is not merely under the stars, it is continuously negotiating with what the stars, remnants, pulsars, binaries, and other engines have already thrown into interstellar space. We are not watching the galaxy from outside. We are embedded in one of its consequences. That embedding is easy to underestimate because the effects are mostly diluted by the time they reach us. Earth's atmosphere protects us. Earth's magnetic field protects us further. The flux is spread out, softened, translated into secondaries. The violence that gave birth to those particles is no longer present in full. What arrives is manageable enough, most of the time, to disappear into background. But the fact that the effects are diluted should not be mistaken for irrelevance. Dilution is exactly what makes the truth psychologically dangerous. It hides the scale of the source behind the mildness of the surviving trace. A cosmic ray at Earth is like ash falling from a fire too distant to light the horizon. The ash does not look like the fire, but it proves the fire exists. And once you start seeing cosmic rays that way, the scientific story acquires a kind of tragic elegance. We do not observe the highest energy processes in the galaxy directly in their full form. We infer them from fragments, after effects, damaged arrivals, photons that just barely survived, patterns in timing, bends in a spectrum, a glow in a molecular cloud that may be the echo of particles accelerated long before. The universe rarely hands over its deepest workings whole. It gives us residue and asks whether we can bear to reason from ruin. That is what high-energy astrophysics is at its most severe. Forensics on a galactic scale. And like all good forensics, it eventually changes how you look at ordinary surfaces. A detective stops seeing a room as a room and starts seeing impact points, traces, trajectories, absences, in the same way, once you learn how cosmic rays forced their way into modern astrophysics. The night sky stops being just a field of stars. It becomes evidence space, every remnant a possible shock, every pulsar a possible wind machine, every binary a possible acceleration geometry, every dense cloud a possible target, every PV photon a possible witness that somehow made it through. The beauty remains, but innocence does not. This is also why the field is still unfinished in such an honest way. We do not yet possess one final clean ledger, assigning every energy range, every particle species, every major contribution to one source class with perfect confidence. The catalogues are growing, the instruments are improving, the lines of evidence are getting sharper. Some sources are already compelling enough to anchor the story. Others remain probabilistic, mixed, ambiguous, or transitional. But that incompleteness is not weakness. It is exactly what you would expect from a science trying to reconstruct a hidden layer of galactic reality from signals that are rare, bent, absorbed, broken, or delayed. The uncertainty here is mature uncertainty, not ignorance standing still, knowledge under pressure, and that is a fitting final intellectual note, because it protects the story from the one thing that would cheapen it: fake closure. There is no honest version of this narrative in which the universe fully surrenders and the mystery becomes a neat catalogue of solved accelerators. What we have instead is stronger. We have a threshold crossed. We know Pevatrons are real. We know they are galactic. We know they exist in multiple physical architectures. We know some sources can accelerate electrons to astonishing energies. We have increasingly persuasive evidence that some can do the harder hadronic work as well. We know the Milky Way is more energetically severe than the visible sky suggests. That is enough to change the world picture, not enough to flatten it. And perhaps that is the right final relationship between human beings and a universe like this. Not mastery, not helplessness. Something more disciplined. The willingness to let explanation deepen reality instead of shrinking it. The willingness to see lawfulness without demanding comfort from it. The willingness to stand under a quiet sky and know that its quiet is a local impression, not a universal condition. Because the deepest fact this story leaves behind is not about a record energy or a named source. It is about perception. What feels distant may already be acting on you. What looks empty may be structured. What appears calm may be full of transfer. And what reaches you may be only the weakest surviving piece of something far more extreme than your senses were built to imagine. And that is why the ending cannot simply rest on astonishment. Astonishment is too easy, too temporary. It treats the discovery like a spectacle when the real effect is slower and more invasive than that. What this story does, if it has worked properly, is not leave you amazed that the universe can build something powerful. It leaves you less certain that your first encounter with reality is ever the real one. Because the opening illusion was never only about the sky. It was about the reliability of appearances. A quiet night, a stable galaxy, empty space between visible things. Those are not exactly false descriptions. They are partial descriptions mistaken for complete ones, and science, at its best, does not merely add facts to that surface. It punctures the authority of the surface itself. It forces a second sight, not mystical vision, not metaphor. A disciplined awareness that what the senses deliver first is often only the human version of the world, not the world on its own terms. Cosmic rays do that with unusual brutality. They arrive as proof that the galaxy is physically active in ways the eye cannot register. They arrive bent by fields, broken by atmosphere, reduced to showers, and still they carry enough information to expose a hidden layer of the Milky Way, one built from acceleration, escape, and transfer. The particles do not just tell us that powerful sources exist. They tell us that our cosmic environment is porous. Energy generated elsewhere does not remain elsewhere. It propagates, it leaks, it enters the local story, which means out there was always less separate than it felt. That is a difficult realization to hold cleanly, because human intuition loves compartments. Earth here, space there, the local world below, the deep universe above, safety in the separation, meaning in the distance. But the atmosphere itself becomes part of the evidence against that divide. It is being struck, ionized, used as a conversion layer where incoming fragments of galactic violence are translated into something our instruments can finally catch. The boundary between local and cosmic is not a wall. It is a medium, and media do not merely separate, they connect. That is what makes this discovery more haunting than a simple catalogue of extreme sources. We did not just find that the universe contains natural accelerators more powerful than anything we can build. We found that their consequences have been arriving at Earth all along. Diluted, yes. Broken, yes. Usually harmless at the scale of everyday life, yes. But arriving. The distance never meant detachment. It only meant that the interaction was subtle enough for us to miss until we learned how to measure it. So the most powerful object in the universe was always a slightly unstable question. Not because it is meaningless, because it tempts the mind toward a single icon when the deeper answer is systemic. The real discovery is not a throne occupied by one ultimate source. It is a universe that repeatedly organizes matter into conditions where acceleration becomes possible, and a galaxy that appears to be full of those conditions in more forms than we once expected. Power here is not a crown. It is a recurring solution, a consequence of lawful structures under stress. That makes the universe feel, in a certain sense, the more impersonal and more intimate at the same time. More impersonal because nothing in this story depends on us. The fields, shocks, winds, jets, and compact remnants do not care that we exist to notice them. The cosmic ray showers would have gone on translating those processes through our atmosphere, whether we ever built detectors or not. The galaxy does not perform for observation. It simply behaves. And more intimate because those behaviors are not sealed away in unreachable abstraction. Their signatures touch our planet, not as myth, not as distant scenery, as arriving particles, as instrumental effects, as physical residue. The universe is never as far away as it looks when one of its processes can still right into your atmosphere after a journey across the Milky Way. This is where the emotional residue sharpens into something calmer and colder than awe. Awe looks upward. Haunting clarity remains after you look back down. Back to the ground beneath the sky. Back to the body that stood under it thinking distance meant insulation. Back to the species that first saw a field of stars and only much later understood that many of the most consequential things happening in that field would be invisible to naked sight. There is a kind of humility in that, but not the soft kind, not the familiar line about human smallness. Smallness is too obvious. The sharper humility is cognitive. The recognition that what feels most natural to perception can be structurally inadequate to reality. And this story earns that recognition, honestly. Not through mystification. Through mechanism. Through Hess climbing into the sky and finding more ionization, not less. Through the century-long failure of charged particles to preserve their route. Through the knee in the spectrum forcing a boundary into view. Through the mountain observatory built because the evidence was too rare and too broken for anything smaller. Through the Pevi photon that turned a hypothesis into an observed regime. Through the gamma ray's straight path. Through the background photons that prevented it from coming from too far away. Through the candidate engines, remnants, pulsars, binaries, clouds, perhaps harsher environments still, all revealing that the Milky Way is less a calm arrangement of lights than an active medium with pockets of severe energy conversion. Nothing in that chain is decorative. That is why the emotional effect lasts. Because the script has not asked you to feel wonder first and then stapled science onto it afterward. The wonder is what the science does when followed to its natural conclusion. The unease is what the evidence deserves. The elegance comes from structure, not inflation. A universe like this does not need help sounding profound. It only needs to be described faithfully enough for its implications to arrive intact. And the final implication is almost painfully simple. What reaches us is only the leak. That may be the cleanest compression of the whole story. A cosmic ray detected near Earth is not the full event, not the source, not the violent environment in which the particle gained its energy. It is what survived distance, magnetic deflection, and atmospheric destruction. It is the remnant of the remnant, a diluted witness, a surviving shard. If the shard is this extreme, then the process that produced it must have been larger than the arrival we measure. The evidence at Earth is already the softened version. The galaxy we can feel directly is therefore the gentle version too. And that is the afterimage the story should leave behind. Not a list of sources, not a final ranking. A changed sky. The same stars as before, but no longer carrying the same meaning. The same Milky Way arching overhead, but now doubled. One visible, one inferred, one made of light, one made of transfer, one calm to the eye, one busy with acceleration, confinement, escape, collision, and fallout. You can still call it beautiful. In some ways it becomes more beautiful, but the beauty hardens, it stops being decorative. It becomes the surface expression of a system whose hidden processes are colder, stranger, and more exacting than the visible sky ever suggested. That is the true destination of the question we began with. Not the identity of one supreme object, but the realization that the universe is built in layers, and the deeper layer is often less comforting and more real. So when you step outside now, and the night seems quiet, that quiet should feel different. Not broken. Translated. Because somewhere in the galaxy, a shock is still trapping particles against a moving front. Somewhere, a pulsar is still bleeding rotational energy into a wind. Somewhere, a compact system is still converting gravity into jets and timing its own violence in the dark. Somewhere, fields are still bending trajectories through interstellar space. Somewhere, gamma rays are still being born with energies too high to travel forever. And somewhere above your head, one of the surviving products of all that labour may already be entering the atmosphere, about to break apart into a shower that no human eye will notice. The stars will not react. The night will keep its composure. And Earth will go on moving beneath a sky that only looks peaceful. Because peace was never the real condition, only the visible one. And that may be the most honest place to end, because it returns us to the opening image without letting it mean what it meant before. The night sky is still there in all the old human ways. It is still where people have always put wonder, loneliness, navigation, mythology, prayer, measurement, longing. It is still the oldest ceiling we know, the oldest distance, the oldest mirror for whatever a civilization happens to feel about its place in things. But after this descent, that ceiling no longer holds. Or rather, it holds differently. What once looked like a backdrop now feels like an interface. What once looked like distance now feels like transmission delayed by scale. What once looked like silence now feels like a limit of the senses, not a property of the world. The stars have not changed. The galaxy has not changed. What changed was the innocence of the first reading. That is what science at its highest level really does. It does not merely add detail to the familiar. Sometimes it takes the familiar away and gives back something harder, truer, and less psychologically accommodating in its place. Cosmic rays did that. Pevatrons did that. The hidden, distributed acceleration architecture of the Milky Way did that. They took one of the calmest images in human experience, a clear night above Earth, and revealed that it was never a complete scene. It was a filtered cross-section, a local rendering of a reality whose deeper traffic does not care whether it is visible to us. Fields bend charged particles whether or not we can picture the field. Shock fronts go on stealing bulk motion and turning it into particle energy, whether or not a human mind has language ready for the process. Pulsars go on shedding rotational energy into relativistic winds. Compact binaries go on converting infall into outflow. Gamma rays go on being born, crossing space, colliding with background light, dying in transit, or just barely surviving long enough to indict a source. And the atmosphere goes on doing what it has always done, taking the surviving fragments and breaking them into showers over our heads. That is the final inversion. For most of human history, the atmosphere felt like the thing that separated us from space, the layer that ended the world and began the heavens. But in this story, it becomes something else, not a border, but an instrument, not a wall, but a translator. It does not stop the universe from reaching us. It converts that reach into a form we can finally detect. It turns cosmic violence into local evidence. So even here, at the end, Earth is not outside the story. Earth is where the story becomes legible. That matters because it rescues the narrative from becoming a mere tour of exotic astrophysical machinery. The real destination was never just to admire the engines. It was to understand that we are downstream from them, protected, mostly, buffered, yes, but not sealed off, never sealed off. The old fantasy of isolation, the idea that the cosmos is out there while the real world is down here, cannot survive a particle that was accelerated somewhere else in the Milky Way and still ends its journey by ionizing the air above this planet. The distance was real. The separation was not. And this is why the final feeling should not be panic. Panic belongs to things that can be resolved with immediate reaction. This story is not about emergency. It is about orientation, about seeing the world more correctly after a long misunderstanding. The proper residue is colder than fear and more durable than amazement. A kind of lucid vertigo. The realization that the visible account of reality is not false enough to be discarded, only incomplete enough to be dangerous if trusted too much. That is the real wound opened by this science. Not that the universe is violent, that it was always violent in lawful, measurable, structurally elegant ways, and we were looking straight through the evidence without knowing what it meant. Now we know a little more of what it meant. We know that the Milky Way contains natural accelerators capable of pushing particles into the peta-electron volt regime. We know that some of those sources can be associated with remnants, pulsars, compact binaries, star-forming complexes, and perhaps still harsher environments under the right conditions. We know that the old image of a mostly tranquil galaxy is physically inadequate. We know that what reaches Earth is not random cosmic noise, but the damaged residue of real processes unfolding elsewhere in our own galactic environment. We know that every incoming particle is, in a strict sense, an emissary of hidden structure. And just as importantly, we know what we do not yet fully know. We do not yet possess a perfect final ledger assigning every contribution, every source class, every energy regime, every particle species with total confidence. The field is still moving, catalogues are still expanding, mechanisms are still being tested against sharper data. Some sources are secure enough to stand as anchors, others remain mixed, transitional, or unresolved. But uncertainty here no longer feels like emptiness. It feels like terrain, real terrain, already partly mapped, extending further into a system whose logic is now impossible to deny. That kind of uncertainty is not a weakness. It is what the edge of reality looks like when measurement has finally become good enough to injure intuition. So the next time the sky feels quiet, that feeling should remain available to you, but thinner, less authoritative. You should still be able to stand under the stars and feel the old human things, but alongside them there should be another awareness now, one that has no need to announce itself loudly, one that simply stays there, underneath the visible scene like a second frequency, that somewhere beyond sight, the galaxy is still accelerating matter to extreme energies, that some of those particles, or the photons and showers that testify to them, are still finding their way into our local environment, that the Milky Way is not a passive backdrop of light, but a living distribution of fields, shocks, remnants, winds, jets, and hidden transfers, that what looks empty may be structured, that what looks calm may be active, that what reaches you may be only the faintest surviving piece of something immense, and that this is not a poetic exaggeration. It is the literal condition. In the end, we did not just find powerful objects. We found out that the galaxy itself had been misread. We found out that the difference between a peaceful sky and a violent one can be nothing more than the bandwidth of your senses. We found out that evidence can be raining through your atmosphere for a century before you learn how to call it by its true name. And we found out that reality does not become smaller when it is explained at depth. It becomes harder to look away from. Because once you understand what cosmic rays really are, not rays, but survivors, not curiosities, but residue, not isolated events, but leaked consequences of hidden accelerators scattered through the Milky Way, then the old image of the heavens cannot quite recover. The stars still shine. The dark still gathers between them. The galaxy still drifts above us in pale light. But now another version of that same sky exists at the same time, one full of invisible trajectories, violent transfers, failed escapes, successful ones, particles bent across magnetic distances, photons born at impossible energies, and showers already beginning over the planet before any human being thinks to look up. And that is the final shift. Not that the universe contains monsters. That reality is deeper, harsher, and more connected than appearance ever suggested. The night sky is still beautiful. It is just no longer innocent,